Good evening, and welcome to The Sleepy Scientist. This is your time to settle in, let the day fade away, and simply listen as we drift through the universe together. Tonight's journey is about the quiet life of a star, a story that stretches across billions of years told in the soft glow of starlight. Before we begin, I would love to know where you are watching from. It is always fascinating to hear which corner of the world you're listening in from. And if you feel like supporting these calming explorations, a like and a subscribe would be wonderful. Thank you so much to those of you who are already subscribed. Your support truly keeps these stories shining. Now, I do hope this video is soothing enough to guide you towards sleep, though perhaps not so captivating that you end up staying awake just to hear how the tale unfolds. If that does happen, at least you will drift off knowing a little more about the universe above. So what does it really mean for a star to live a life? From a distance, a star appears eternal. It rises and sets with the rhythm of the sky, glowing with the same familiar light night after night. Yet behind that steady shine lies a story as dramatic and intricate as any life on Earth. Stars are born, they grow, they change, and in their final acts they shape the universe itself. Every atom of carbon in your body, every trace of oxygen in your breath, every spark of iron in your blood was once forged in the heart of a star that lived and died long before our sun was born. This story is as old as time itself, stretching back to the very first stars that flickered into being when the universe was young and dark. To follow the life of a star is to follow the history of everything. Galaxies, planets, oceans, forests, and even you. It is the slow but unstoppable rhythm of creation and transformation. In the chapters ahead, we will wander through the star's entire existence, from its silent beginnings in dark, drifting clouds of gas, to the brilliant blaze of its middle years, and finally to the quiet or cataclysmic ends that scatter the seeds of new worlds. Along the way, we will discover how stars not only illuminate the cosmos, but also make it possible for life itself to exist. This journey is not rushed. Stars live on timescales far longer than human imagination can easily hold, and so tonight we will follow them at a pace suited for rest, gentle, steady, and calm. So let us begin by stepping into the universe's great nursery, where the first whispers of a star are waiting in the silent darkness. If you look up at the night sky, it is easy to imagine stars as tiny pinpricks of light scattered across a black canvas, each one neat and self-contained. But in truth, the beginnings of a star are far from orderly. They start in places so vast and so dark that even light seems reluctant to escape. These are the molecular clouds, sometimes called stellar nurseries, and they are among the most mysterious landscapes in the cosmos. A molecular cloud is not a tidy little puff of mist drifting through space. It is colossal. Some stretch for dozens, even hundreds, of light years across. They are made of hydrogen, the simplest and most abundant element in the universe, along with helium and a sprinkling of heavier elements and dust. From afar, they appear as ghostly silhouettes against the brighter background of starlight. Through a telescope, they take on shapes that can be surprisingly familiar. A horse's head, an eagle's wings, a giant pillar that seems to stand upright against eternity. It is easy to see why astronomers, poetic at heart, have given them such names. Inside these clouds, however, the view would be very different. Imagine drifting through the darkness, surrounded by particles of gas so spread out that you could travel billions of miles before bumping into another atom. Yet despite this thinness, the sheer scale of these clouds means that they contain enough material to make not just one star, but thousands. A single cloud might hold the mass of 1 million suns, waiting patiently in the cold. Cold, indeed, is the key word. These regions are some of the chilliest places in the universe. Temperatures sink to just a few dozen degrees above absolute zero. At such low energies, atoms move sluggishly, and the hydrogen molecules can huddle together in pairs, forming the molecular hydrogen that gives these clouds their name. It is within this deep chill that the conditions become just right for gravity to do its quiet work. Gravity is patient. It does not rush, nor does it announce itself with a bang. Over millions of years, the tiniest fluctuations, perhaps from a nearby supernova, perhaps from the slow dance of galaxies colliding, disturb the cloud just enough to make certain pockets denser than others. These denser knots act like seeds. As their gravity grows slightly stronger, they begin to draw in more gas, and with each atom that falls inward, the pull grows stronger still. It is a slow spiral, a feedback loop that begins almost imperceptibly, but becomes unstoppable once it gains momentum. From our distant vantage point, this process is invisible to the naked eye, but scientists observing through radio telescopes can detect the faint whispers of molecules deep within the cloud. These instruments tune into the wavelengths of light invisible to our eyes, revealing complex patterns of carbon monoxide, ammonia, and even organic molecules, the building blocks of life. It is humbling to think that, in the darkness where stars are born, chemistry is already hard at work, sketching the outlines of futures not yet imagined. One of the most iconic images of a stellar nursery comes from the Hubble Space Telescope, the Pillars of Creation. These towering structures of gas and dust in the Eagle Nebula look almost sculpted, as if some celestial artist had reached out with a brush. Each pillar is many light years tall, with tips that glimmer faintly as newborn stars within push their light outward. The image has become a kind of cosmic postcard, a reminder that creation is both beautiful and grand. Dust plays an unexpectedly vital role in this story. Tiny grains of carbon and silicates, no larger than smoke particles, float throughout the clouds. Though small, they absorb and scatter light, allowing the interiors of these clouds to remain shielded from external radiation. This creates safe, dark cocoons where the fragile beginnings of stars can take hold. Without dust, the relentless glare of surrounding starlight might evaporate these nascent cradles before they had a chance to grow. Dust, in this sense, is the curtain that allows the great play of stellar birth to begin unseen. If you could listen to these regions, not with ears but with instruments designed to pick up vibrations in gas, the sounds would be haunting. They are not the roars of explosions but the soft whispers of turbulence, the low groan of matter moving against itself, the faint hiss of atoms colliding. All of it unfolds on timescales so long that, compared to human lifetimes, it may as well be frozen. A star's birth is not measured in years or centuries, but in millions of years. It is creation in slow motion. The scale is difficult to grasp, but think of this. A human lifetime might span 80 or 90 years. In that same time, a star-forming cloud has barely shifted at all. Even over thousands of years, the changes are subtle. Only with the patient gaze of science, stitching together observations across generations, can we truly appreciate the progress. It is like watching a glacier carve a valley. Glacial indeed, but with results that endure for ages. And yet, for all its slowness, the process is inevitable. Gravity does not lose interest. Once a knot begins to collapse, it draws in more and more matter, creating regions so dense that the outer cloud cannot resist their pull. Eventually these knots fragment into clumps, each one destined to become a star. Some will grow into giants that blaze blue and live short, furious lives. Others will settle into modest, long-lived forms, like our own sun. Many will remain small, glowing dimly as red dwarfs that outlast nearly everything else. The diversity of stars, from titans to runts, all begins here in the same dark nurseries. There is a quiet poetry to the idea that stars are born not in brilliance but in obscurity. The light that will one day travel across galaxies begins in darkness, hidden from view. Like seeds buried in soil, stars begin their lives unseen, nourished by forces both simple and profound. Only after patience, collapse, and heat will they reveal themselves to the cosmos. It is tempting to think of these clouds as merely functional, raw material waiting to be used. But they are more than that. They are places of mystery, of beauty, and of potential. They remind us that the universe is not static, but forever in the act of becoming. Within their veils of gas and dust lies the promise of new suns, new worlds, and perhaps new forms of life. In the stillness of a molecular cloud, you find both silence and anticipation. The hydrogen waits, the dust drifts, gravity pulls ever so gently. And somewhere, in a pocket of darkness, the first heartbeat of a future star begins to stir. Deep within the quiet of a molecular cloud, something subtle begins to change. What was once an almost uniform spread of gas and dust starts to gather, pulled inward by gravity's patient hand. At first, it is imperceptible. Nothing seems to move, and the great veil of gas drifts as it always has. But gravity is relentless. Given enough time, even the faintest imbalance turns into motion, and soon the invisible hand of attraction begins to shape the future. The collapse of matter within a cloud is not like a dramatic plunge or a sudden landslide. It is more like a sigh that never ends, an inward drifting of atoms pulled toward a common centre. Each hydrogen atom, light as it is, feels the tug from all directions. But where the density is even slightly higher, the pull is stronger. It is in these places that the collapse accelerates. The clumps gather mass, and as they do, they grow hungrier, pulling in more gas from their surroundings. It is a cosmic version of the rich getting richer, except in this case the wealth is gravity. As the cloud contracts, something remarkable begins to happen. Potential energy, the energy stored in the mere arrangement of mass, starts to transform. When gas falls inward under gravity, it gains speed. The collisions between particles grow more frequent, more energetic, and heat is the inevitable outcome. What began as one of the coldest places in the universe slowly warms, though warm in this sense is still bitterly cold by earthly standards. But compared to the near absolute zero chill of the surrounding cloud, the heart of the collapsing clump becomes an oasis of rising temperature. To understand this, it helps to imagine squeezing a sponge. The more you press, the harder the water pushes back, forced into a smaller volume. With a collapsing gas cloud, it is not water that pushes back, but pressure itself. Gas atoms resist being crowded together, and as gravity forces them closer, the pressure builds. Pressure and temperature are partners in this dance. Higher pressure means particles are colliding more often, and with each collision, energy is shared and spread. That shared energy manifests as heat. At first, the growing clump remains hidden. Surrounding dust keeps the warmth from escaping, cloaking the nascent object in shadow. But in the heart of the clump, the temperature creeps higher and higher, inching toward the critical threshold where fusion might one day ignite. This object, not yet a true star, is what astronomers call a protostar, a body in the making, glowing faintly from the energy of collapse. The physics of this stage is both simple and elegant. Gravity pulls inward, pressure pushes outward. The balance between the two dictates the speed and nature of the collapse. If gravity were to win completely, the cloud would fall to a singular point. But pressure always pushes back, and the battle creates an equilibrium that slows the collapse, allowing it to unfold over millions of years rather than moments. This balance is delicate, and even the smallest changes in mass or temperature can tip the scales toward a new phase of development. During this time, the protostar gathers a surrounding disk of material, a kind of flattened halo formed by the conservation of angular momentum. Every particle in the collapsing cloud carries a tiny bit of spin, and as the gas falls inward, that spin is conserved, just as a figure skater spins faster when pulling their arms inward. The result is a whirling disk of dust and gas encircling the central mass. From this disk, planets may one day form, but for now it is a silent companion to the star's birth. Inside the protostar itself, layers of gas are compressed to densities unimaginable by human standards. The pressure becomes so high that atoms are stripped of their electrons, and the gas behaves more like a soup of charged particles than a simple mixture of atoms. The core grows denser and hotter, radiating energy outward not from fusion but from the sheer force of gravitational contraction. This radiation pushes against the surrounding material, creating a faint but growing glow. If you could peer into such a cloud, the protostar would appear as a hidden ember, shining dimly in the infrared spectrum. The process is not entirely smooth. Bursts of energy can cause jets of material to shoot out from the poles of the protostar, narrow beams of plasma streaming across space for light years. These jets carve through the surrounding cloud, sometimes punching holes in the veil of gas and dust. Though they look dramatic in images, they are simply another expression of balance. As the star gathers mass, it must shed some of its angular momentum, and these jets provide the release. They are in essence the newborn's first cries into the cosmos. It is worth remembering just how slow this drama unfolds. From the moment a dense clump begins to collapse until it becomes a stable protostar, millions of years may pass. Entire civilizations could rise and fall, continents could shift, ice ages could come and go, and still the star would only just be approaching its birth. To the universe, this is a blink. To us, it is eternity. And yet, for all the vastness of time, the laws that govern this process are familiar. The same principles that heat the air when you pump a bicycle tyre, or that warm your hands when you rub them together, also warm the core of a collapsing cloud. The difference is simply scale. Instead of a few molecules in your hands, there are trillions upon trillions of them, and instead of a few seconds of rubbing, there are millions of years of contraction. The ordinary becomes extraordinary by virtue of its cosmic stage. As the protostar grows, it begins to push back against the collapse. The radiation it emits warms the surrounding gas, and that heat adds pressure, slowing the infall of material. Eventually, a balance is reached where the inward pull of gravity is matched by the outward push of energy. The protostar is not yet a true star, for the nuclear fires in its core have not been lit. But it has become a distinct entity, no longer just part of the cloud, but a body with its own glow, its own boundaries, and its own future. This stage is filled with anticipation. The protostar is like a match poised against the box, waiting for the final strike. The heat in the core continues to build, the pressure grows, and with each passing moment the likelihood of ignition increases. But whether that ignition will succeed depends on mass. Only if the protostar gathers enough material will the temperature in its core climb high enough to begin fusing hydrogen to helium. For smaller clumps, the fires never catch, and the result is a brown dwarf, a failed star that glows faintly but never shines like its larger cousins. Gravity has done its work, sculpting raw gas into a dense, glowing seed. Heat has emerged from collapse, an ember of energy that promises greater brilliance ahead. The protostar waits, suspended between potential and reality, a reminder that even the quietest forces can, given time, reshape the universe. In the darkness of a molecular cloud, a faint glow begins to emerge. What was once only a knot of collapsing gas has become something more defined, more alive. The protostar is awakening. Still hidden from ordinary sight by the dusty veil that surrounds it, this young object has taken on a shape, a character, and a restless energy that announces its presence to the cosmos. At the centre lies the dense core, its temperature rising with every heartbeat of gravitational collapse. Around it, a wide and graceful disk of gas and dust whirls in orbit, flattened by the spin of the collapsing cloud. This is the circumstellar disk, a natural outcome of angular momentum, and it is more than just decoration. Within this disk, grains of dust bump, stick, and clump together, setting the earlier stage for planets, moons, and asteroids. In a sense, while the star is preparing for its debut, the seeds of an entire solar system are quietly being sown. The disk is not silent. Friction between particles, shocks of energy, and radiation from the growing protostar stir it constantly. The inner regions heat up, glowing in infrared, while the outer regions remain cold and shadowy. Spirals of material may form, sculpted by turbulence, or by the gravitational pull of clumps that one day could become planets. For now, it is chaos with a pattern, a cosmic whirlpool governed by the laws of physics but looking every bit like a work of art. Above and below the disk, something even more dramatic occurs. The young protostar begins to launch powerful jets of plasma from its poles, shooting into space at hundreds of kilometers per second. These jets are narrow, collimated streams of matter stretching light years into the void. They pierce through the cocoon of dust and gas, carving bright tunnels visible in telescope images as Herbig-Haro objects. To the human eye, they look almost painterly, streaks of luminous colour against the dark. To physics, they are the natural release valves of angular momentum, a way for the newborn star to shed excess spin and stabilise itself. The interplay of disk and jet, of collapse and outflow, creates a scene that is both violent and beautiful. The star-to-be is not yet steady, but it is no longer only a collapsing cloud. It has become an actor on the stage of the cosmos, announcing itself with light and motion. Inside the core, conditions are shifting. The temperature, which once hovered at a few thousand degrees, climbs steadily higher. With every atom that falls inward, the compression grows more intense and collisions become fiercer. At around 10 million degrees, the simplest and most important transformation in the universe begins to whisper. Hydrogen nuclei start to fuse into helium. At first, the fusion is tentative. Only a trickle of protons collide with enough force to overcome their mutual repulsion. But even this trickle releases energy, and that energy radiates outward, adding to the glow of the protostar. It is as though a tiny spark has been struck in a cold fireplace. The wood is piled high, the tinder is dry, and now the flame begins to spread. This transition from collapse-powered heat to fusion-powered light is one of the great turning points in cosmic history. It marks the moment when a protostar ceases to be a mere object of potential and becomes a true star in the making. Gravity no longer acts alone. Nuclear forces join the dance. The outward pressure from fusion starts to balance the inward crush of gravity, and for the first time the young star finds something resembling stability. Still, this balance is not perfect at first. The protostar quivers, sometimes swelling outward, sometimes shrinking back as the forces adjust. These oscillations can last for thousands of years, a period when the star flickers and shifts in brightness. To us this may sound unstable, but to the star it is merely the final adjustments before settling into its long and steady adulthood. The awakening of a protostar is also the awakening of light. Though dust still hides the star's visible glow, radiation in the infrared and radio wavelengths escapes freely. Telescopes tuned to these signals can peer through the murky clouds, revealing hundreds of protostars scattered throughout regions like the Orion Nebula. Each one is a spark waiting to ignite, a future sun surrounded by the promise of planets. It is a humbling reminder that our own solar system began in just such a place 4.5 billion years ago. Consider for a moment the scale of this process. A single protostar may take millions of years to fully ignite, yet in that span, it sets into motion events that will ripple across billions of years. The disk that now swirls around it may one day coalesce into worlds, some barren, some ocean-covered, perhaps even some alive. All of it depends on the simple fact that hydrogen is beginning to fuse, that the furnace of creation has finally found its flame. As the protostar grows in strength, it also grows in character. The colour of its light, the rhythm of its jets, the structure of its disk, all of these will help determine what kind of system it will host. A massive protostar, far larger than our Sun, will blaze fiercely and live briefly. A smaller one may glow gently for trillions of years. Each is unique, yet all share the same origin story, born from collapse, nurtured by gravity and awakened by fusion. There is a quiet paradox here. The birth of a star is both violent and serene. On the one hand, jets roar into space, disks swirl with turbulence, and gravity crushes matter into densities far beyond imagination. On the other hand, from the vastness of the cosmos, it all unfolds in near silence, with a grace that seems more like a slow dance than a battle. It is a reminder that beauty often lies not in the absence of chaos, but in the harmony that emerges from it. The moment hydrogen begins to fuse is sometimes described as ignition, but it is not a sudden spark like a match. It is more like dawn breaking over a long night. At first, the light is faint and tentative, then stronger, then unstoppable. With fusion underway, the protostar is no longer just awakening. It has taken its first breath as a true star, ready to shine for eons to come. Yet for now it remains wrapped in its dusty cradle, its light mostly hidden from ordinary view. The jets continue to carve paths outward, the disk continues to swirl, and the core continues to burn ever hotter. The protostar is awake, restless and growing, its journey only just begun. At last, the star finds its balance. After millions of years of collapse, turbulence and restless shifting, the core has reached the point where fusion burns steadily. Gravity pulls inward, trying to crush the mass into an ever smaller point, while the outward pressure from nuclear reactions pushes back with equal strength. The tug-of-war finally reaches equilibrium, and in that balance a star is born into what astronomers call the main sequence. This is the long calm, the great middle act of a star's life. It is a period that can last for billions upon billions of years, so long in fact that it dwarfs every human timescale. Civilizations may rise and vanish, continents may drift across oceans, and entire species may come and go, yet the star remains unbothered, shining with steady light. At the heart of this serenity lies a single process, the fusion of hydrogen into helium. It is deceptively simple. 4 hydrogen nuclei, which are just protons, collide and merge through a series of steps, eventually forming a helium nucleus. In the process, a tiny fraction of mass is converted into energy, according to Einstein's famous equation, E equals mc squared. Though the fraction of mass lost is vanishingly small, the amount of energy released is enormous, because the speed of light squared is an unimaginably large number. This is the secret engine of the stars, and it is remarkably efficient. The photons created in the core do not immediately race outward like a beam from a flashlight. Instead, they embark on an agonizingly slow journey. The interior of a star is so dense that light cannot travel far without being absorbed and re-emitted by other particles. A single photon may spend hundreds of thousands of years bouncing around inside before finally escaping into open space. By the time it reaches the surface, it has lost much of its original energy, transformed into the warm visible light that streams across the void. When you step into a shaft of sunlight, you're feeling the end of a journey that began long before the first humans walked the Earth. From a distance, a star in its main sequence phase appears serene, but the interior is a cauldron of motion. Convection churns in the outer layers of some stars, carrying heat upward in great rolling cells. In more massive stars, radiation dominates, with photons streaming outward through layers of gas. The details differ, but the result is the same, the steady release of energy that keeps the star shining. This constancy is the reason life on planets like Earth is possible. A star in the main sequence does not flicker wildly or erupt unpredictably. Its output is steady enough to provide warmth and light for billions of years, allowing oceans to remain liquid, atmospheres to remain stable, and ecosystems to evolve. In a universe filled with violent events, supernova, black holes, and galaxies colliding, the main sequence is a rare gift of stability. It is in many ways the quiet heart of cosmic time. Not all stars live the same kind of calm. The lifespan of a star depends almost entirely on its mass. Paradoxically, the largest stars live the shortest lives. A star many times more massive than the Sun burns through its hydrogen at a furious rate. Blazing blue and bright, but exhausting its fuel in only a few million years. By contrast, the smaller stars, the red dwarfs, sip their hydrogen so slowly that they may shine for trillions of years, far longer than the current age of the universe. Our sun sits comfortably in between, destined to enjoy a main sequence life of about 10 billion years, of which roughly half has already passed. The colours of stars reflect their temperatures during this phase. Hot, massive stars glow blue or white, cooler ones glow orange or red, and stars like the Sun fall in the gentle middle with a yellow-white hue. These colours are not just aesthetic, they tell astronomers about the physics of the star, its mass, temperature and age. A glance at the night sky reveals a rainbow of stellar lives quietly unfolding above. It is easy to think of this long calm as uneventful, but subtle changes are always underway. As hydrogen fuses into helium, the composition of the core slowly shifts. Helium, being denser, accumulates in the centre, while hydrogen is consumed. This alters the balance of pressure and temperature, causing the star to grow gradually brighter over time. The Sun, for example, is about 30% brighter now than it was when life first began on Earth. It has changed so slowly that no living thing could notice from one generation to the next, but across geological ages the difference becomes profound. In the calm of the main sequence, stars become the architects of everything else. Their light sculpts the shapes of nebulae, their winds blow through interstellar space, and their gravity anchors planets into orbits where new stories can unfold. The heavy elements forged in earlier generations of stars are recycled into new systems, so that every atom in your body has likely passed through at least one star's lifetime. You are, quite literally, living starlight given form. It is worth pausing to imagine the patience of a main sequence star. For us, a century feels long, and a millennium is almost unimaginable. For a star, 1,000 years is barely a tick of the clock, an instant in its steady shining. To describe a star as middle-aged may mean it has already been burning for 5 billion years and still has another 5 billion ahead. This perspective stretches our sense of time until it feels almost endless. Yet for all its enormity, the life of a main sequence star is not abstract. It is deeply personal. Every breath of oxygen you take is thanks to stars that came before. Every glance at the night sky connects you to a story that has been unfolding since before the Earth even existed. The calm light that spills through your window each morning is the sun's steady gift, a reminder of the quiet generosity of stars in this stage of life. The main sequence is, above all, a meditation on endurance. It is the long inhale and exhale of the universe, the steady heartbeat that allows galaxies to shine and planets to flourish. A star in this phase is not rushing toward an ending, nor is it trapped in its beginning. It is simply being, radiating warmth, and holding its balance for as long as its fuel allows. In the grand story of the cosmos, this is the chapter that lasts the longest, the one written in the patient language of billions of years. Stars spend the majority of their existence here, quietly burning hydrogen into helium, casting light across the void and supporting the fragile possibility of life. It may not be as dramatic as birth or as spectacular as death, but without this long calm, there would be no time for worlds to grow, no chance for life to wonder about the stars at all. A main sequence star is the universe at its most generous. It gives without demanding, it endures without complaint, and it shines without rest. Its calm is not emptiness but fullness, the fullness of light, of warmth, and of time itself. And in that fullness we find not only the story of stars, but the story of everything that has ever looked up at them. Deep inside the core of a star, the journey of light begins. It starts as a single photon, born in the fusion of hydrogen into helium. In that moment, a fraction of mass is transformed into pure energy, a tiny spark created in conditions so hot and so dense that ordinary matter is stripped down to its barest essence. That photon might seem destined to streak straight outward into space, but the reality is far stranger. The interior of a star is not transparent like air, nor even translucent like frosted glass. It is an almost impenetrable ocean of plasma, where atoms are stripped into nuclei and electrons, and where particles jostle shoulder to shoulder. For a newborn photon, there is no easy path forward. It collides almost immediately with an electron or a nucleus, absorbed and then re-emitted, sometimes in a new direction, sometimes with slightly different energy. It takes a step, then tumbles back, then veers sideways. Its path is a random walk, a cosmic pinball game with no clear end. Because of this relentless scattering, the outward progress of a photon is achingly slow. A journey that would take mere seconds if space were empty instead stretches into hundreds of thousands of years. Some photons may wander for more than 1,000,000 years before finally reaching the surface. To imagine this is to think of light not as a racing arrow, but as a patient wanderer, stumbling through a labyrinth so vast that its exit is measured not in miles but in epochs. And yet the star never falters. With trillions upon trillions of photons all taking their meandering paths, the combined effect is a steady outward flow of energy. This is what keeps the star balanced, what allows it to shine with calm and constant brightness. Each photon's journey may be uncertain, but together they create the illusion of stability, the unwavering light that travels across space to reach distant worlds. As photons migrate outward, they also change character. A gamma ray born in the core carrying enormous energy is scattered so many times that by the time it nears the surface, it may have been transformed into lower energy light. The photon that finally escapes as visible light, gentle enough to warm a planet's surface, is the descendant of countless collisions. In a way, sunlight is recycled starlight, energy that has been passed from particle to particle like a message whispered through an ancient crowd. When at last a photon reaches the photosphere, the visible surface of the star, it is released into the vast openness of space. Here, the rules change entirely. No longer trapped in the dense plasma, the photon is free. In less than 8 minutes, a ray of light from our sun can travel across the 93 million miles to Earth. After hundreds of thousands of years spent crawling through the star's interior, its final leap to a human eye is almost instantaneous. The sheer scale of this difference is almost comic. Imagine being stuck in traffic for 500,000 years, only to find that the final leg of your journey takes less than the time it takes to boil a kettle. That is the life of a photon. Its long exile inside the star is followed by a sudden exhilarating sprint through the emptiness of space. But the story does not end with its release. Once photons leave the star, they travel unhindered, carrying information about the star's temperatures, composition, and age. Every colour in the light tells a story. Blue light reveals heat, red light reveals cooler regions, and the subtle dark lines in the spectrum show which elements are present in the star's atmosphere. Astronomers reading starlight are like detectives poring over an ancient manuscript, deciphering secrets written in invisible ink. The scale of these journeys is almost beyond imagination. Light from the sun takes those 8 minutes to reach Earth, but light from the nearest star beyond our solar system takes over 4 years. The glow from the Orion Nebula, where new stars are born, left more than 1,000 years ago, before the first castles were built in Europe. The faint light from the Andromeda Galaxy began its trip more than 2 million years ago, when early humans were still shaping stone tools. When you look at the night sky, you are seeing not the present but a vast collection of pasts, woven together in a single view. Some photons travel even farther. Light from distant galaxies captured by telescopes today may have been travelling for billions of years, carrying with it a record of the early universe. These ancient photons began their journeys when the cosmos itself was young, long before Earth formed, long before the sun existed. They are messengers from a time when galaxies were still finding their shape, when the universe was bathed in a softer, more uniform glow. And remarkably, photons do not grow tired. Unlike us, they do not age with travel. A photon leaving a star will continue onward until it is absorbed, whether that happens in the atmosphere of a planet, in the dust of a nebula, or in the mirrors of a telescope. Some may wander through intergalactic space for billions of years without encountering anything at all, their energy stretching and reddening as the universe expands, but never extinguished until the moment of contact. It is strange to think that the light spilling through your window each morning began its existence before the human story even started. The warmth on your skin is the final chapter of a tale that may have taken hundreds of thousands of years to unfold. Every ray of sunlight is history made visible, a message written in the language of photons and delivered across space and time. Stars, then, are not just objects that shine, they are storytellers. Each photon is a sentence, each wavelength a phrase, carrying news of the cause fires and the elements within. When we gaze at the stars, we're not just looking outward but backward, into eras long gone, illuminated by light that has crossed the gulf of time to meet our eyes. There is something quietly profound in this. The next time you see a star twinkle, you might consider the immense patience of the photons that make that shimmer possible. Born in fire, trapped in darkness, wandering for ages, they finally escape and race across the cosmos just to greet you. They remind us that even the smallest speck of light carries with it the vastness of history, the endurance of time, and the promise that the universe, in all its enormity, is still capable of whispering directly into our lives. A star may look like nothing more than a glowing dot in the night sky, a quiet decoration scattered across the heavens, but each one is far more than a lamp in the darkness. Stars are engines of creation, the architects of galaxies, and the foundries that forge the very atoms of our bodies. Without them, the universe would be an empty, silent expanse of hydrogen and helium. With them, it becomes a stage filled with complexity, beauty, and life. When a star burns hydrogen in its core, it is not simply producing light and heat, it is also transforming the chemistry of the cosmos. Fusion in the heart of a star takes the simplest element, hydrogen, a lone proton, and weaves it into helium, a slightly more elaborate nucleus. Over time, as stars grow older and hotter, they begin to craft heavier elements. Helium can fuse into carbon, carbon into oxygen, oxygen into neon and magnesium, and onward up the chain to silicon and iron. This process, known as stellar nucleosynthesis, is the cosmic alchemy that fills the periodic table. Yet even the most massive stars cannot forge everything. Iron marks a kind of barrier, a point where fusion no longer produces energy, but instead consumes it. To go beyond iron, the universe relies on stellar death. In the explosive finale of a supernova, temperatures and pressures soar to unimaginable levels, and in those moments the heaviest elements are born: gold, platinum, uranium, and more. These are the treasures of the cosmos scattered across space in the debris of shattered stars. It is humbling to realize that the gold in a wedding ring or the calcium in your bones was once inside a star. Long before Earth existed, long before the sun itself was born, ancient stars lived, burned, and died, leaving behind the raw ingredients that would one day form planets, oceans, forests, and people. To say that we are made of stardust is not poetry, it is fact. Every breath, every heartbeat, every thought is built upon atoms that were forged in stellar furnaces. Stars do not only shape the chemistry of the universe, they also shape its structure. Galaxies, those vast swirls of stars and dust, are held together in part by the gravity of their stellar populations. Without stars, galaxies would be little more than diffuse clouds of gas drifting through the void. But as stars form, their gravity anchors the surrounding matter, sculpting the grand spirals, elliptical clusters, and irregular clouds that we observe across the night sky. Even within galaxies, stars influence the rhythm of creation. When massive stars form, they flood their neighborhoods with powerful winds of charged particles, and blasts of ultraviolet light. These stellar winds carve out cavities in surrounding clouds, compressing nearby gas and sometimes triggering the birth of new stars. In this way, one generation of stars sparks the next, a cosmic cycle of cause and effect that shapes the destiny of galaxies. Our own sun, though ordinary by galactic standards, exerts a profound influence on its surroundings. Its gravity holds the planets in their orbits, binding together the solar system like pearls on a thread. Its light provides the energy that fuels weather, photosynthesis, and life itself. Without the sun's steady presence, Earth would be nothing more than a frozen rock wandering aimlessly through space. The sun is a reminder that stars are not distant abstractions. They are the anchors of worlds, the centres around which stories unfold. But stars also influence the universe on scales so vast they defy easy imagination. In the early cosmos, shortly after the Big Bang, the universe was a sea of hydrogen and helium, with few structures to break the monotony. It was the first stars, igniting in that darkness, that began to shape the universe into something recognisable. Their ultraviolet light reionized the surrounding gas, clearing the cosmic fog and allowing light to travel freely. Their supernovae seeded space with heavier elements, enriching the raw material for future generations of stars and planets. Their gravity helped clump matter into the galaxies we see today. In this sense, stars are the universe's great sculptors. They take the raw simplicity of primordial hydrogen and carve it into complexity. They give rise not only to planets and life, but also to the very conditions that allow the cosmos to be visible at all. Without them, space would remain a dim and formless expanse, silent and unchanging. With them, it becomes a canvas alive with light and story. Consider the delicate balance at work here. Too few stars, and the universe would lack the elements needed for chemistry and biology. Too many massive stars and their violent deaths might tear apart young galaxies before life could take root. The universe, as it turns out, is tuned by the rhythms of stellar birth and death, a balance that allows both destruction and creation to coexist in a kind of cosmic harmony. The legacy of stars is written everywhere we look. The iron rails of a train track, the silicon in a computer chip, the oxygen in your lungs, all of it passed through the life cycle of a star. To walk on Earth is to walk on the ashes of ancient suns. To gaze at the night sky is to look not only at distant lights, but also at your own origin story. And yet, for all their grandeur, stars do not act with intention. They do not know they're shaping galaxies or forging the atoms of life. They simply follow the laws of physics, gravity pulling inward, fusion pushing outward, matter rearranging itself under pressure and heat. It is a process both inevitable and miraculous. From simple rules emerge outcomes as profound as gold jewellery, seashells and human curiosity. There is a quiet humour in the idea that some of the most precious things we prize, the sparkle of a diamond ring, the shimmer of platinum, the glow of a fireplace's embers, are byproducts of stars living their lives. Stars are, in a way, the universe's most generous artists, scattering beauty across space without ever pausing to admire it themselves. To appreciate how stars shape the universe is to see the cosmos not as a static backdrop, but as an ongoing performance. Each star is both a participant and a creator, contributing to the symphony of galaxies, elements, and life. Their light is the music, their gravity the rhythm, and their deaths the dramatic crescendos that give rise to new beginnings. The next time you look at the night sky, try to imagine the work being done in silence above. Every twinkle is a forge, every glow a beacon of creation, every faint shimmer a reminder that the universe is alive with transformation. The atoms that make you akin to those distant lights, born in fire, carried across space, and gathered into the shape of your body. Stars did not just shape the universe. In a very real sense, they shaped you. When you look up at the night sky, it is tempting to think that all stars are the same, tiny white specks scattered across the darkness. But with a careful eye, or a good telescope, you will notice that stars come in different hues and levels of brightness. Some glow faintly red, others shine with a blue-white brilliance, and in between are shades of gold, amber, and pale yellow. These differences are not just pretty variations, they reveal the very nature of the stars themselves. Astronomers make sense of this variety through a tool known as the Hertzsprung-Russell diagram, often shortened to the H-R diagram. It may sound technical, but at heart it is a kind of cosmic family portrait, a way of arranging stars according to their brightness and temperature. Along one axis is luminosity, how much light a star emits. Along the other is temperature, which correlates with colour. When stars are plotted in this way, they fall into distinct patterns that tell the story of their lives. The largest group of stars, including our Sun, line up along a broad diagonal band called the main sequence. Here, stars spend the majority of their lives quietly fusing hydrogen into helium. The position of a star along this sequence depends almost entirely on its mass. A massive star burns hotter and appears bluer, while a small star glows cooler and appears redder. Mass, in this sense, is destiny. At the smallest end of the main sequence are the red dwarfs. These stars are the most common type in the universe, making up nearly 3/4 of all stars. They are small, faint and cool, glowing with a dim red light that is almost invisible to the naked eye. Yet their modesty grants them extraordinary longevity. A red dwarf burns its hydrogen fuel so slowly that it can shine for trillions of years, far longer than the current age of the universe. If cosmic endurance were a competition, red dwarfs would win without question. Somewhere out there, red dwarfs born not long after the Big Bang are still burning steadily, patient guardians of time itself. At the opposite extreme are the blue giants. These stars are massive, luminous, and incredibly hot, glowing with a brilliant blue-white intensity. Their light can be tens of thousands of times brighter than that of the Sun, and their size can be dozens of times larger. But such brilliance comes at a cost. Blue giants burn through their fuel with reckless speed, living only a few million years before meeting a dramatic end as a supernova. They are the fireworks of the cosmos, dazzling, spectacular, but fleeting. Between these extremes lies a whole spectrum of stars. There are orange dwarfs, slightly smaller and cooler than the Sun, which might live for tens of billions of years. There are yellow stars like our Sun, middle-aged and steady, providing the conditions for life on orbiting planets. There are subgiants which have begun to drift off the main sequence as they exhaust their core hydrogen, and giants, which swell to enormous sizes as they begin fusing helium and heavier elements. Each type of star has its place on the H-R diagram, and each follows a predictable path across it as it ages. The colours of stars are not just matters of temperature but also of physics. A hot star emits more energy at shorter wavelengths, which is why it appears blue or white. A cooler star emits more energy at longer wavelengths, making it appear orange or red. It is the same reason a stove burner glows red when warm and white when extremely hot. When you see a red star in the night sky, you're essentially seeing the cosmic equivalent of a glowing ember. When you see a blue star, you're seeing the universe's equivalent of a blowtorch. Our Sun sits comfortably in the middle of this spectrum. It is a G-type star, modest in size, modest in brightness, and modest in temperature. It glows with a gentle yellow-white light, steady enough to support life for billions of years. If it were much larger and hotter, it might burn out too quickly for life to develop. If it were much smaller and cooler, its habitable zone might be so narrow that Earth-like worlds would struggle to stay warm. In a sense, the Sun is the cosmic equivalent of porridge that is neither too hot nor too cold, just right. The H-R diagram also reveals the stages of stellar evolution. As stars age and exhaust their hydrogen, they drift off the main sequence into new regions of the diagram. Some swell into red giants, expanding to hundreds of times their original size. Others collapse into white dwarfs, small but incredibly dense remnants that glow faintly as they cool. A star's journey across the diagram is like a biography written in colour and brightness, a record of its birth, maturity, and eventual decline. One of the most fascinating aspects of the H-R diagram is how it brings order to what might otherwise seem chaotic. Look up at the sky, and you see stars scattered without pattern, each one a mystery. Plot them on the diagram, however, and a structure emerges. The main sequence, the giant branch, the white dwarf region, these are not random but the natural outcomes of stellar physics. The diagram is a reminder that even in the apparent chaos of the cosmos, patterns and order can be found. The variety of stars also shapes the variety of planets and life that may exist. Red dwarfs, though faint, often host planets that huddle close to their warmth. Some of these planets may be tidally locked, with one side bathed in eternal day and the other in endless night. Blue giants, though short-lived, may trigger bursts of star formation around them, with their powerful winds and supernova explosions. Yellow stars like the Sun provide steady energy for billions of years, creating the stability needed for ecosystems to flourish. Each colour of star is like a different note in the symphony of the universe, contributing its own tone and rhythm. Even the distribution of stars in galaxies reflects these differences. In spiral arms, where new stars are born, you find clusters of bright blue giants shining like cosmic beacons. In the older central bulges of galaxies, redder stars dominate, ancient and enduring. The mixture of colours tells the story of galactic history, of cycles of birth and death, of generations of stars shaping the destiny of entire systems. It is easy to forget when gazing at the night sky that those faint points of light are not uniform. Each has its own character, its own size, its own destiny. Some will outlive the universe as we know it, glowing dimly for trillions of years. Others will flare brilliantly and vanish in what, by cosmic standards, is the blink of an eye. Our sun, steady and unassuming, sits between these extremes, a quiet star with just enough warmth and just enough time to allow a small rocky planet to grow forests, oceans and civilizations capable of looking back at it in wonder. The colour and size of a star are not superficial details. They are the fingerprints of physics, the signatures of mass, temperature and age. They tell us not only what a star is now, but also where it has been and where it is going. The next time you notice a star that glows a little redder or bluer than the others, you're not just seeing a difference in shade. You're seeing a life lived on a different time scale, a destiny shaped by mass and heat, and a place on the grand diagram that maps the universe's most luminous inhabitants. The night sky is, in truth, a rainbow written in stars. From the faintest red dwarfs to the blazing blue giants, from our modest yellow sun to the countless varieties in between, each star adds its own hue to the canvas of the cosmos. Together, they paint a portrait of a universe that is as orderly as it is beautiful, a universe in which every colour tells a story of time, of energy, and of life itself. There is one star that matters to us more than any other, a star so familiar that it almost disappears into the background of daily life. It rises each morning, arcs across the sky, and sinks again in the evening. It warms our skin, powers the growth of plants, drives the winds and currents of the oceans, and sets the rhythm of our days. It is the sun, an ordinary star by cosmic standards, and yet extraordinary in its role as the quiet heart of our world. The sun is not especially large. It is not particularly hot nor especially bright compared to the stars scattered across the galaxy. Astronomers classify it as a G-type main sequence star, one of countless millions of its kind. And yet, from our vantage point, it is everything. At about 100 times wider than Earth, and more than 300,000 times as massive, it dominates the solar system with its gravity. Every planet, moon, asteroid and comet traces its path around the sun, held in orbit by its steady pull. Without it, there would be no Earth, no oceans, and certainly no life to contemplate its light. The sun's warmth is both gentle and relentless. At its core, hydrogen nuclei fuse into helium at a staggering rate, releasing energy that eventually emerges as sunlight. Every second, the sun converts nearly 4 million tons of mass into pure energy. That number is almost impossible to imagine, and yet from 93 million miles away, this immense furnace provides just the right amount of heat and light to keep Earth comfortably habitable. It is a cosmic coincidence that our planet sits at precisely the right distance, in the so-called habitable zone, where water can remain liquid and life can thrive. It is easy to take this balance for granted. The sun does not flicker dramatically. It does not blaze unpredictably or fade without warning. Instead, it shines with quiet consistency, a steady beacon across the billions of years of Earth's history. When life first stirred in the oceans nearly 4 billion years ago, the sun was there. When dinosaurs roamed the land, it was there. When the first humans gazed upward in awe, the same star lit their nights and warmed their days. The continuity is comforting, a reminder that amidst all the changes of history, some things remain steadfast. Yet the sun is not static. It evolves, albeit on timescales so vast that no human could ever notice. As it fuses hydrogen into helium, its core gradually changes in composition. Helium accumulates, altering the balance of pressure and temperature, and the sun slowly grows brighter over time. In its youth, it was about 30% dimmer than it is today, which makes the persistence of liquid water on Earth in those early days a puzzle for scientists. The faint young sun paradox, as it's called, remains one of the intriguing questions about our planet's past. Looking ahead, the sun still has plenty of fuel. It is roughly halfway through its main sequence life, with about 5 billion years left before it begins to run short on hydrogen. For now, its fusion furnace hums along steady and generous, but eventually the balance will shift. The core will contract, temperatures will rise, and the outer layers will swell outward, transforming the sun into a red giant. In that distant future, the inner planets, perhaps even Earth, may be engulfed. Oceans will boil away, skies will glow, and the calm, familiar sun will take on a very different form. The end, however, will not be violent compared to the fate of massive stars. Our sun is not large enough to explode as a supernova. Instead, it will shed its outer layers in a series of delicate outflows, creating a glowing shell of gas called a planetary nebula. The core that remains will collapse into a white dwarf, a small but incredibly dense remnant roughly the size of Earth. That white dwarf will shine faintly for billions of years more, cooling slowly until it becomes a dark ember, a black dwarf hidden in the depths of time. This quiet ending is fitting for such a modest star. No fireworks, no cataclysm, just a graceful transition from one state to another. The elements it leaves behind, carbon, oxygen, nitrogen, will drift into interstellar space, enriching the galaxy and providing the building blocks for new stars and planets. In this way, even in death, the sun will continue to shape the cosmos, joining the endless cycle of stellar birth and renewal. What makes the sun extraordinary is not its size or brightness, but its stability. In a galaxy filled with stars that live short, brilliant lives, the sun has chosen a longer, quieter path. Its main sequence lifespan of about 10 billion years provides a window of time wide enough for life to emerge, evolve, and flourish. It is hard to overstate the importance of that patience. Without it, Earth's story might have ended before it began. For ancient peoples, the sun was more than a source of light. It was a god, a symbol, a ruler of the heavens. Cultures across the world built monuments aligned to its rising and setting, marking solstices and equinoxes with stone and ritual. It was celebrated in myth as a fiery chariot, a radiant deity, or the eternal eye of the sky. Even today, long after science has explained its nature, the sun retains its power as a symbol of life and renewal. We still speak of dawn as a beginning, of sunshine as joy, of sunset as peace. There is something deeply personal about our relationship with this star. It shapes not only the physics of our world, but also the rhythms of our lives. Its daily rise and fall sets the pace of work and rest. Its seasonal tilt brings warmth and cold, growth and dormancy. The sun has been a companion for all of human history, its light woven into every story, every painting, every poem about the sky. It is as ordinary as the clock on the wall, and as extraordinary as the fact that without it, we would not exist. When you feel the warmth of sunlight on your face, you are feeling the product of nuclear fusion that began in the sun's core hundreds of thousands of years ago. A photon born in that fiery furnace wandered for eons through dense plasma, before escaping into space, racing across the void, and finally landing gently on your skin. That warmth is a gift of time and distance, the simplest yet most profound connection between human life and the cosmos. To reflect on the sun is to reflect on balance. It is large enough to hold the planets in orbit, yet not so large as to burn out quickly. It is bright enough to sustain life, yet not so intense as to destroy it. It has been steady for billions of years, and it will remain steady for billions more. It is, in every sense, an ordinary star, and that ordinariness is precisely what makes it so extraordinary. The sun is our quiet guardian, our dependable companion, and our link to the greater cosmos. Its story reminds us that the universe does not always need grandeur to be magnificent. Sometimes, the greatest wonders are the ones that shine every day, unnoticed until we pause to look up. When we do, we see not just a ball of plasma in the sky, but the very heart of life itself, glowing with patience, endurance, and quiet grace. For most of its life, a star is the very definition of stability. It shines steadily, converting hydrogen into helium with a patience that spans billions of years. To any observer, it appears eternal, as though it will go on glowing forever. But even stars, as vast and enduring as they seem, cannot escape the slow passage of time. Subtly, almost imperceptibly, change creeps in. The fuel that powers the steady furnace begins to dwindle, and with that shortage comes transformation. At the heart of every star is its engine, the fusion of hydrogen into helium. For ages this process has been reliable, balancing the inward pull of gravity with the outward push of energy, but hydrogen is not infinite. As the star consumes its fuel, the central core fills with helium ash, material too light to fuse further under existing conditions. The ratio of hydrogen to helium shifts, and suddenly the equilibrium that seemed so perfect begins to falter. The first sign of aging is the contraction of the core. As hydrogen thins out, there are fewer fusion reactions to push outward. Gravity, which never relents, takes the opportunity to squeeze the core tighter. With that squeeze comes heat, and the temperature in the centre of the star climbs higher than ever before. Ironically, even as the fusion of hydrogen slows, the star's outer layers respond to this heating by expanding, and the star grows brighter. The changes are gradual on a human timescale, but dramatic on a cosmic one. Our own sun, for instance, is already brighter now than it was when Earth first formed. In its youth, it shone at about 70% of its current luminosity. Over the last 4.5 billion years, it has steadily increased in brightness, and it will continue to do so as it edges toward old age. This brightening is slow enough that life has had time to adapt, but it is also inexorable. A few billion years from now, the sun's light may grow so intense that Earth's oceans could evaporate, long before the sun becomes a giant. The changes are not only in brightness but also in size and structure. As the core contracts, the surrounding shells of hydrogen become hotter, and fusion shifts into these outer layers. The star develops a layered interior, a helium core surrounded by a shell where hydrogen continues to fuse. This change alters the balance of pressures inside, causing the outer regions to swell and the star's surface temperature to shift. Some stars redden as they age, drifting off the main sequence into new stages of their evolution. For stars more massive than the Sun, these changes are accelerated and amplified. A heavy star burning through its hydrogen at a reckless pace finds itself running low far sooner. When its core contracts, the heat rises so quickly that new types of fusion reactions ignite. Helium begins to fuse into carbon and oxygen, and the star's structure becomes even more complex, with multiple shells of fusion burning simultaneously. These layers resemble the rings of an onion, each shell producing different elements that will one day be scattered into space. The physics of this transformation are elegant in their inevitability. The balance of a star is always a contest between gravity, pulling inward, and energy, pushing outward. As long as fuel is abundant, the balance holds steady. But as fuel diminishes, gravity gains the upper hand and the star must adjust. That adjustment is never a single event, but a gradual process, a slow reshaping of the star's interior and exterior. From the outside, the change may look like a gentle swelling or a slight shift in colour, but inside, the structure is being rewritten. For smaller stars, those that glow as red dwarfs, the story unfolds differently. Their slow consumption of hydrogen means they can remain in their main sequence state for trillions of years, far longer than the universe has even existed so far. None of them have lived long enough to show us their eventual fate, but for stars like the Sun, and especially for larger stars, the signs of aging are well known. The calm of the main sequence eventually gives way to a more restless era, one where brightness varies, sizes shift, and the certainty of stability fades. It is fascinating to consider how subtle these changes are when viewed from Earth. Even as the Sun brightens, it does so on scales of tens of millions of years. No single sunrise looks different from the last. No single year brings a noticeable shift. It is only when measured across vast spans of time that the changes become apparent. This slow pace is deceptive, for the consequences are immense. A few percentage points more brightness from the Sun could alter climates, shift ecosystems, and eventually render Earth uninhabitable. Stars, for all their steadiness, carry the seeds of dramatic transformation. As a star continues to age, the helium core at its centre grows more massive and dense. Gravity squeezes it into extraordinary states, where matter is packed more tightly than in any earthly material. This core, unable to fuse further under current conditions, becomes a kind of weight dragging the star into its next stage. It is as though the star carries its past with it, unable to discard the remnants of the fuel it has already burned. Astronomers often describe stars as living things, with births, lives, and deaths. If so, the aging of a star is like the first signs of grey in its hair, or the subtle slowing of its stride. It is not yet at the end, but the signs are clear. Time is passing, and the great transformation is on its way. Unlike humans, stars age with immense patience, their decline measured not in decades but in eons. Still, the direction is the same. The long calm is over, and the slow march toward change has begun. There is a quiet beauty in this inevitability. The elements that will one day enrich space, forming planets and life, are being prepared in these aging hearts. The changes may mean instability for the star itself, but for the cosmos they mean creation. Every shift in brightness, every contraction of the core, is a step towards scattering carbon, oxygen, and heavier elements across the galaxy. The star's aging is not only an ending but also the beginning of countless new stories. When you gaze at the stars in the night sky, you're not only seeing them as they are, but also catching glimpses of them in transition. Some are still in the calm of their youth, others are quietly aging, their light subtly altered by the changes within. They remind us that even the most steadfast of things is subject to time, that stability itself is a phase, not a permanent state. The slow change of a star as it ages is both melancholy and magnificent. Melancholy, because it signals the eventual end of a steady light we rely on. Magnificent, because it is through this process that the universe renews itself. Aging stars are the crucibles of creation, their transformations the source of the matter that makes worlds and living beings possible. In their decline, they shape the future of the cosmos, leaving behind not silence, but legacy. To watch a star age is to witness the rhythm of the universe, not in sudden bursts, but in patient, unyielding steps. The core contracts, fusion shifts, brightness grows. Slowly, quietly, inevitably, the star walks its path through time, carrying within it the destiny of all that will follow. There comes a moment in a star's life when the quiet patience of the main sequence ends, and change can no longer be postponed. The supply of hydrogen in the core dwindles until it is no longer enough to keep the balance steady. Gravity, ever persistent, squeezes the helium-rich core tighter, and in doing so sparks a chain of events that reshapes the star in dramatic fashion. What was once a modest, steady sphere begins to swell outward, transforming into a red giant. To describe a star as swelling does not quite capture the enormity of what is happening. Imagine a sphere growing so vast that it multiplies its own diameter hundreds of times. The Sun, for instance, will one day expand so far that Mercury and Venus will almost certainly be engulfed, and Earth itself may be swallowed by its fiery atmosphere. Even if Earth survives, its surface will be scorched beyond recognition. The ocean's long gone, the rocks glowing under the unbearable heat. From a distance, however, the transformation is strangely graceful. The star's outer layers puff outward like a balloon, glowing red and cool compared to the fierce heat of the core. The term gentle roar suits this stage perfectly. From the outside, the expansion appears slow and smooth, a gradual swelling that takes millions of years. From the star's perspective, however, the core is roaring with new intensity. The contraction raises the temperature to the point where helium fusion can finally ignite, fusing 3 helium nuclei into carbon. This process, known as the triple alpha reaction, pours out energy, and that energy pushes against the outer layers, inflating the star like a great luminous lantern in the sky. Despite its swollen size, the surface of a red giant is surprisingly cool compared to its earlier phase. Instead of glowing white or blue, it now glows with a reddish-orange hue, the telltale sign of lower surface temperature. Yet this coolness is deceptive. The sheer size of the star means that its luminosity is immense, thousands of times greater than before. What it lacks in surface heat, it makes up for in sheer scale, casting light and warmth across vast distances. If you could stand on a planet orbiting a red giant, assuming it had not already been engulfed, the view would be astonishing. The star would dominate the sky, filling it with a crimson glow. Shadows would stretch long and faint, colours would appear washed in red, and the heat would be relentless. The night sky, if it could still exist in such a system, would be bathed in perpetual twilight from the swollen star's light. It would be both beautiful and apocalyptic, a vision of grandeur that no living being could survive. The physics behind this expansion is a kind of cosmic balancing act. As the core contracts and grows hotter, the outer layers are pushed outward by the sheer pressure of the energy being released. These layers are tenuous, stretched thin over a vast distance, so much so that the outer atmosphere of a red giant can be blown away by stellar winds. Material that was once securely part of the star is carried off into space, forming shells of gas and dust that enrich the interstellar medium. The star, in growing older, becomes generous, scattering the ingredients for future generations of stars and planets. This generosity is one of the paradoxes of the red giant phase. To an orbiting planet, the swelling is catastrophic. Worlds are scorched or consumed, their atmospheres stripped, their surfaces sterilized. And yet, from the perspective of the galaxy, this destruction is a gift. The expelled gases and heavier elements will drift into space, mixing with cold clouds where new stars will one day form. In the death throes of one star lie the seeds of countless others. The transformation into a red giant also alters the star's internal structure. Fusion no longer happens just in the core but also in shells around it. Hydrogen burns in a shell surrounding the helium core, while helium itself begins to fuse in the very centre. In more massive stars, additional shells ignite, fusing carbon, oxygen and heavier elements. The star becomes a layered structure, like a cosmic onion, each shell burning a different fuel. It is an intricate, fiery architecture, one that marks the final act of stellar life before collapse or quiet fade. Though the red giant phase signals the beginning of the end, it can last for a surprisingly long time. For a star like the Sun, this stage will endure for perhaps 1 billion years. That is long enough for its inflated form to dominate the sky of its solar system, long enough for its stellar winds to carve vast clouds into space, and long enough for the universe to prepare for its next act. In cosmic terms, it is not a fleeting moment but a significant chapter, one that shapes the destiny of everything nearby. The sheer size of red giants makes them some of the most recognizable stars in the night sky. Betelgeuse, the bright red shoulder of Orion, is a classic example. If it were placed at the center of our solar system, its swollen body would extend beyond the orbit of Mars. Another is Antares, the heart of Scorpius, glowing like a red ember against the darkness. These stars are reminders that the fate awaiting the Sun is not unique. It is the common destiny of stars of a certain mass, a transformation written into their very physics. For humans, the idea of the Sun becoming a red giant carries a quiet weight. It is a glimpse of the distant future, a time when Earth as we know it will no longer exist. Oceans will boil away, continents will glow, and even the most resilient forms of life will be swept aside. Yet this vision is not one of despair. It is a reminder of the impermanence of worlds and the continuity of the cosmos. What ends here will begin again elsewhere, in new stars, new planets, and perhaps new forms of life. There is a strange comfort in this thought. The Sun, so steady and unassuming now, carries within it the promise of transformation. Its gentle roar as a red giant will not be the end of the story but the passing of a torch. The carbon and oxygen it creates will drift into space, waiting to be gathered by the next generation of stars. The atoms that make up our bodies may someday be part of another world, warmed by another sun, contemplated by other minds. A red giant is not just an old star. It is a cosmic artist, painting the universe with colour and scattering the materials of creation. Its swelling form is both an ending and a beginning, both destruction and gift. To watch a star become a red giant is to witness the universe itself breathing, expanding outward, exhaling the elements of life into the great darkness. So when you look at Betelgeuse or Antares glowing in the night sky, remember that you are seeing the gentle roar of time itself. These stars are showing us what lies ahead, not just for them, but for our own sun. They are reminders that even the quietest stars carry within them the power to transform worlds, to end stories, and to begin new ones, all in the vast, patient rhythm of the cosmos. Inside an aging star, the story grows more complex. For billions of years, hydrogen fusion has been the steady heartbeat, a simple reaction transforming the universe's most basic element into helium. But as the hydrogen in the core dwindles, the star faces a challenge: how to continue producing the energy it needs to resist gravity's unyielding pull. The answer lies in unlocking new fuels, and in doing so the star's interior begins to take on an intricate layered structure, a cosmic onion glowing with fire. The first great shift comes with helium. When the contracting core becomes hot enough, around 100 million degrees, helium nuclei begin to collide with enough force to overcome their natural repulsion. This process, called the triple alpha reaction, fuses 3 helium atoms into a single carbon nucleus. With the addition of a 4th helium, oxygen is born. Suddenly the star has a new way to generate energy, and its life extends into another chapter. This moment is often dramatic for stars like the Sun. Because helium fusion begins abruptly in a degenerate core, where matter is packed so tightly that pressure no longer depends on temperature, the ignition can happen explosively in what astronomers call a helium flash. In reality, the star does not blow apart, but the sudden onset of fusion releases an enormous burst of energy that reconfigures the star's interior, stabilizing it into a new balance. The outer layers settle again, and the star continues on, powered now by helium burning at its core. But helium, like hydrogen before it, is finite. Once much of it has been consumed, the core contracts further, heating to even greater extremes. Around it, shells of fusion continue to burn, with hydrogen fusing in one layer and helium fusing in another. The result is a star with multiple active zones, each layer generating its own energy. It is here that the onion-like structure begins to take shape, a nested sequence of shells, each burning a different fuel. In more massive stars, the process continues step by step. After helium comes carbon, fusing into neon, magnesium and sodium. With further contraction and heating, oxygen fuses into silicon and sulfur. Finally, silicon itself fuses into iron. Each stage requires higher temperatures and shorter timescales. While hydrogen fusion might last for billions of years, carbon burning might endure for only thousands, oxygen for mere months, and silicon for just days. The progression is a race, the star sprinting through fuels faster and faster as it approaches its inevitable end. The layering of these reactions creates a structure unlike anything found on Earth. Imagine slicing through a massive star in its final stages. At the very centre lies an iron core, inert and unyielding. Around it burns a shell of silicon fusion, then shells of oxygen, neon, carbon, helium, and finally hydrogen at the outer edge. It is a fiery nesting doll of elements, each layer hotter and denser than the one outside it, each working under conditions that stagger the imagination. For stars of smaller mass like our Sun, the layering is less elaborate. The Sun will never reach the temperatures required to fuse carbon or oxygen. It will end its days after the helium phase, leaving behind a core composed largely of carbon and oxygen. Yet even this modest layering shapes the destiny of everything around it. The carbon and oxygen produced in the Sun's heart will one day drift into space, forming the raw material for new planets, new oceans, and perhaps even new forms of life. The onion-like interiors of stars are hidden from us, but their effects can be observed. As the star fuses different fuels, it swells, contracts, and changes in brightness. Pulsations ripple outward, and strong stellar winds strip material away into space. Astronomers peering through telescopes can measure these changes in light and deduce what is happening deep within. The cosmos, though silent, leaves clues for those who know how to listen. The physics that drives this layering is elegant in its simplicity. Gravity squeezes the core tighter as each fuel runs out. Higher pressure demands higher temperatures, and higher temperatures allow new kinds of fusion to begin. But there is always a cost. Each successive stage produces less energy per unit of fuel, and each stage is shorter lived. It is as if the star, once patient and steady, begins to rush toward its finale, burning through its options with increasing haste. What makes this process so profound is the legacy it leaves behind. Every element beyond helium in the periodic table owes its existence to these layers of stellar fusion. The carbon in the graphite of a pencil, the oxygen in the air, the magnesium in chlorophyll, the silicon in sand. All of these were forged in stars. Without the layering of stellar interiors, the universe would remain chemically impoverished, a simple mix of hydrogen and helium without the complexity needed for life. The grandeur of a star in this phase is difficult to overstate. Its outer layers can swell to such vast proportions that it engulfs nearby planets. Its light can blaze with the luminosity of tens of thousands of suns. Yet beneath that radiant exterior lies a fragile balance, a structure stacked precariously as each new fuel source runs its course. The star is living on borrowed time, propped up by layers that cannot last forever. And when at last the final fuel is spent, the outcome depends on the star's mass. For smaller stars, the outer layers drift gently away, leaving a white dwarf behind. For massive stars, the onion collapses in on itself, triggering the explosive release of a supernova. But before that final act, the star's interior is a masterpiece of layering, a natural fusion reactor operating on a scale beyond imagination. To picture it is to see a kind of cosmic clock, ticking down with each shell that ignites and fades. Hydrogen gives way to helium, helium to carbon, carbon to oxygen and beyond. Each layer marks the passage of stellar time, each a reminder that even the brightest of stars carries within it the inevitability of change. Yet there is also beauty in this inevitability. Without it, there would be no diversity of elements, no richness of worlds, no possibility of life. The onion-like interiors of stars are not just stages of decline, but engines of creation, quietly preparing the universe for its next chapter. When you breathe in oxygen, or see the sparkle of silicon crystals, or feel the calcium in your bones, you are sharing in the legacy of these layers. The star, in its aging complexity, becomes not just a light in the sky, but a sculptor of existence itself. Each shell, each layer, is a workshop of creation, building the raw materials for futures yet to come, and as the star nears its end, it does so not in silence but in generosity, leaving behind a universe richer than before. So the next time you look at the stars and think of them as simple points of light, remember the hidden layers within. Beneath that glow is an intricate architecture, a cosmic onion burning with fusion, a furnace where the very fabric of matter is stitched together. Stars are not just shining spheres. They are layered stories, each shell a chapter, each element a word, all part of the grand narrative of the universe. In the grand theatre of the cosmos, not every star ends its life in a blaze of fireworks. The majority, in fact, slip quietly into obscurity, leaving behind not explosions but embers. These are the small to medium stars, suns like our own, and the countless red and orange dwarfs scattered throughout the galaxy. Their destiny is not a supernova, but a slow, graceful retreat into silence, culminating in the creation of white dwarfs. The story begins when the star exhausts the last of its nuclear fuel. Hydrogen has long since been consumed in the core, helium has fused into carbon and oxygen, and the temperatures required for heavier fusion are out of reach. The star cannot push any further. Gravity, which has always waited patiently in the background, now takes centre stage. Without the support of fusion, the core collapses under its own weight, but instead of collapsing endlessly, it encounters an extraordinary resistance, not from heat or pressure, but from the strange rules of quantum mechanics. Here, the electrons themselves step in as guardians. In the crowded heart of the dying star, electrons are pressed so close together that they cannot occupy the same state. This resistance, known as electron degeneracy pressure, halts the collapse. The result is a white dwarf, a stellar core about the size of Earth, but with a mass comparable to that of the Sun. Imagine compressing an entire star into a sphere no bigger than our planet. A teaspoon of its matter would weigh tons, dense beyond anything in the everyday world. Though small, a white dwarf shines brilliantly at first. It still glows from the residual heat of its former life, its surface blazing at tens of thousands of degrees. But there is no fusion left to replenish that heat. The white dwarf is not a star in the traditional sense anymore. It is a remnant, radiating away its stored energy. Over billions of years it cools and dims, fading from white to yellow, from yellow to red, and eventually to black. This cooling process is unimaginably slow. White dwarfs may linger for longer than the current age of the universe, which is why astronomers have never observed a fully cooled black dwarf. The cosmos is simply not old enough for one to exist. Every white dwarf we see today is still glowing, however faintly. its silence illuminated by the memory of fusion long past. For planets orbiting such a remnant, the change would be profound. Worlds once bathed in steady sunlight would find themselves in perpetual twilight, their skies dominated not by a golden star, but by a small, brilliant point of light. Heat would vanish, oceans would freeze, and atmospheres would collapse. The system that once thrived around a living star would become a frozen archive, a monument to what once was. And yet, even in this quiet, there is beauty. The light of a white dwarf is sharp and pure, the glow of a cosmic ember shining against the blackness. White dwarfs also tell a deeper story. Their compositions reveal the processes that took place in the hearts of stars. Many are made primarily of carbon and oxygen, the ashes of helium fusion. Some, the remnants of lower mass stars, are composed mainly of helium. Others, formed from more massive stars, contain traces of neon and magnesium. By studying them, astronomers can piece together the history of stellar life and death, much like archaeologists reading ancient inscriptions. There is also a limit to what white dwarfs can endure. If the mass of the collapsing core exceeds about 1.4 times the mass of the Sun, electron degeneracy pressure can no longer hold back gravity. This limit, known as the Chandrasekhar limit, marks the boundary between stars that end as white dwarfs and those that collapse further into neutron stars or black holes. Stars below this threshold fade quietly. Those above it explode or implode with drama. The universe, as always, balances modesty and spectacle. Our own sun will one day join the ranks of the white dwarfs. About 5 billion years from now, after swelling into a red giant and shedding its outer layers, the sun will leave behind a glowing white dwarf at its core. For billions more years it will shine faintly in the dark, a final echo of the star that once illuminated Earth. Long after our planet is gone, long after the galaxy itself has changed beyond recognition, the sun's remnant will still be cooling in silence. The destiny of red dwarfs, the most common stars in the universe, is even more remarkable. Because they burn their hydrogen so slowly, they can shine for trillions of years before ever reaching the white dwarf stage. None of them have lived long enough to die yet. The universe is simply too young. In the far future, long after larger stars have vanished, red dwarfs will still be burning faintly. When they finally fade, they too will leave behind white dwarfs, filling the cosmos with a quiet sea of stellar remnants. In a way, white dwarfs are the great librarians of the universe. They preserve the history of stellar life in their compositions, in their cooling rates, and in their very existence. They are silent archives, glowing pages written in heat and light, waiting to be read by those who know how. Each one is a story of patience, endurance, and the inevitability of change. Though they may seem like endings, white dwarfs also contribute to beginnings. In rare circumstances, a white dwarf in a binary system may accrete matter from its companion star. If it gathers enough material to surpass the Chandrasekhar limit, it will ignite in a type Ia supernova, a brilliant explosion that scatters heavy elements into space and serves as a cosmic yardstick for measuring distances across the universe. Even in their quietude, white dwarfs hold the potential for sudden, spectacular transformation. But most white dwarfs will not explode. They will simply fade, cooling imperceptibly over eons until their light is gone. This slow decline is not tragic but poetic. A white dwarf is a star that has given all it could, that has lit worlds and forged elements, and now rests in quiet dignity. It is the final whisper of a life lived in light, the last chapter of a story that has already shaped galaxies. When you look at the night sky, you are likely seeing white dwarfs among the stars. They do not stand out with brilliance like blue giants, nor do they inspire myth like the red glow of Betelgeuse. They are the quieter members of the stellar family, overlooked yet ever present. Their modest glow is a reminder that not every ending must be loud to be meaningful. The fate of ordinary stars is not destruction, but endurance. They burn patiently, fade gently, and cool slowly into silence, and in that silence lies a kind of serenity. White dwarfs are the embers of the universe glowing softly in the dark, testaments to the quiet persistence of matter and time. Their story is not of drama but of calm, not of sudden endings but of gradual farewells. And perhaps in that quiet we find a reflection of our own lives, finite, fleeting, but woven into the great continuity of the cosmos. There are few spectacles in the universe more dramatic than the death of a massive star. For millions of years it has burned with intensity, fusing hydrogen, helium, carbon, oxygen, and heavier elements in an ever-accelerating race against time. Its layered interior becomes a furnace of shells, each producing new elements in turn, until at last it reaches the final barrier. Iron. Unlike lighter elements, iron does not release energy when fused. Instead, it absorbs it. This is the end of the line, the point at which even the mighty power of fusion can no longer hold back gravity. When the star can fuse no more, its balance collapses. Gravity, which has always pressed inward with silent persistence, now rushes to claim its victory. The iron core shrinks catastrophically in a fraction of a second, collapsing at speeds that defy comprehension. Electrons are forced into protons, creating neutrons and releasing a torrent of neutrinos that flood outward through the star. The outer layers, suddenly unsupported, plunge inward, smashing into the dense core. In that moment, the star's structure tears apart in one of the most violent events in the cosmos, a supernova. To call it an explosion hardly does it justice. In a single instant, the star releases more energy than our sun will radiate over its entire 10 billion year lifespan. The brilliance of the blast can outshine an entire galaxy, making the supernova visible across millions of light years. For weeks or months, it burns with astonishing brightness, a beacon in the night sky that ancient civilizations sometimes recorded without knowing its origin. To those who saw it without explanation, it must have looked like a new star suddenly appearing, a messenger of the heavens blazing into existence. But behind the spectacle lies a profound act of creation. During the explosion, temperatures soar to billions of degrees, and the shock waves racing through the star-forge elements that could never have been created in normal stellar fusion. Gold, platinum, uranium, and many other heavy elements are born in this furnace of chaos. When the star finally tears itself apart, these elements are flung into space, scattered across the galaxy like cosmic seeds. Every piece of jewellery, every circuit board, and every drop of blood rich with iron owes its existence to such an event. Without supernovae, the universe would be chemically impoverished, a dull place of hydrogen and helium. With them, it becomes rich with complexity and potential. The aftermath of a supernova is as striking as the explosion itself. Expelled gas and dust expand outward, forming glowing remnants that can persist for thousands of years. The Crab Nebula, for example, is the remnant of a supernova recorded by Chinese astronomers in the year 1054. Through telescopes, it appears as a delicate web of filaments glowing in vivid colours, each hue representing different elements, oxygen, sulfur, hydrogen, drifting through space. These remnants are not just beautiful, they are the raw material from which new stars and planets will one day form. In their destruction, massive stars ensure the birth of future generations. At the heart of the chaos lies what remains of the star's core. If the collapsing mass is below a certain threshold, it stabilizes as a neutron star, an object so dense that a teaspoon of its matter would outweigh mountains. If the mass exceeds that limit, even neutron pressure cannot resist gravity, and the core collapses further into a black hole. Thus, the death of a massive star often gives birth to some of the most exotic objects in the universe, places where the familiar rules of physics bend and break. Supernovae are not rare by cosmic standards, though from Earth they seem extraordinary. In our galaxy alone, Astronomers expect one to occur every 100 years or so, though dust and distance often hide them from our view. In other galaxies, powerful telescopes routinely capture these sudden bursts of light. They are reminders that the universe is not static but alive with change, punctuated by moments of brilliance amid long stretches of calm. These explosions are also vital to the very structure of galaxies. The shock waves they produce stir and compress interstellar gas, triggering the collapse of new star-forming clouds. Without supernovae, galaxies might stagnate, their gas lying dormant. With them, galaxies are continually renewed, their cycles of birth and death sustained by the violent ends of massive stars. In this way, supernovae are not just spectacular events, but essential engines of galactic ecology. Even from a safe distance, the sheer power of a supernova is difficult to imagine. If one occurred within 30 light-years of Earth, its radiation could strip away our atmosphere and sterilize the planet. Fortunately, no such threat looms nearby. The massive stars capable of producing supernovae are rare, and none lie dangerously close. Instead, we can appreciate them as distant phenomena, cosmic fireworks that illuminate the dark without imperiling our fragile world. To study supernovae is to study both life and death. They represent the end of a star's journey, the failure of its ability to resist gravity. Yet they also represent the beginning of countless others, scattering elements and energy that give rise to new systems. They are destructive and creative in equal measure, embodying the duality that seems to pervade the universe. For all their violence, there is also poetry in these explosions. Imagine a star that has lived for millions of years, burning furiously, shaping its surroundings with light and heat. At the end, it does not simply fade. It leaves in a single moment a legacy that stretches across time, the elements of life, the materials of planets, the sparks of new suns. Its brilliance is a farewell and a gift, a reminder that endings can also be beginnings. When you look at the night sky and see stars scattered across the darkness, know that some of them are destined for this fate. Somewhere in Orion, or Scorpius, or any of the other constellations, massive stars are nearing the end of their fuel, quietly preparing for the day they will explode. One night, perhaps tomorrow, or perhaps in 1,000 years, their light will flare, visible even to the naked eye, a sudden message across space and time. Supernovae are not just spectacular events for astronomers to measure, they are the universe's way of recycling, of ensuring that matter does not remain locked in stars forever. Without them, there would be no Earth, no oceans, no forests, no people. The gold on your finger, the oxygen in your lungs, and the iron in your blood all testify to the brilliance of stars that died long before the sun was born. The death of giants may seem violent and final, but in truth it is a continuation of the cosmic story. Through supernovae, the universe ensures its own renewal, weaving endings into beginnings and destruction into creation. They are not simply explosions, but the heartbeat of the cosmos, pounding loudly and briefly before fading back into silence. And in that silence, the legacy of their brilliance lingers, shining on in the stars, the planets, and the life that carries their atoms forward. When a massive star ends its life in a supernova, the drama is not always the final act. Amid the chaos, the core that once powered the star may survive in a radically altered form. Crushed by gravity to a degree that defies ordinary imagination, it becomes something new, something so strange that it seems more like a thought experiment than a real object. This is the neutron star, a remnant of extraordinary density, a place where the familiar rules of matter are rewritten under immense pressure. A neutron star begins when gravity overwhelms the collapsing core of a massive star, but not enough to force it into a black hole. The iron core shrinks until electrons and protons are squeezed together, merging into neutrons. The result is an object only about 20 kilometers across, yet containing more mass than the Sun. Imagine compressing a mountain into a thimble, or an entire city into the size of a sugar cube. That is the scale of a neutron star. A single teaspoon of its material would weigh billions of tons. Though tiny compared to the star that birthed it, a neutron star is anything but insignificant. Its surface gravity is so intense that if you dropped an object from a height of 1 meter, it would strike the surface at close to the speed of light. Its magnetic fields can be trillions of times stronger than Earth's, bending particles and light in ways that defy intuition. It is, in essence, matter at its most extreme. The universe's way of testing how far physics can be pushed. But neutron stars are not static. They spin, and often they spin with dizzying speed. As the core of the star collapses, its rotation accelerates, much like an ice skater spinning faster as they draw in their arms. A neutron star may rotate dozens, hundreds, or even thousands of times per second. Some of them emit beams of radiation from their magnetic poles, which sweep across space like the beams of a lighthouse. When these beams cross Earth, we see them as regular pulses of light or radio waves. These objects are called pulsars, and they are among the most precise clocks in the universe. The discovery of pulsars in the late 1960s was so surprising that astronomers briefly wondered if they might be signals from extraterrestrial civilizations. The pulses were that regular, repeating with machine-like precision. But the explanation was even more astonishing. Natural lighthouses powered by the spin of neutron stars. Each rotation brings the beam into view, creating a rhythmic flash that can be timed down to fractions of a millisecond. Some pulsars are so steady that they rival the accuracy of atomic clocks on Earth. To contemplate a neutron star is to step into the realm of extremes. On the surface, the gravity is so strong that mountains can only rise a few millimeters before collapsing under their own weight. The crust may be made of an exotic lattice of nuclei, stronger than steel yet fragile in strange ways. Deeper down, neutrons form a superfluid, a bizarre state of matter that flows without resistance. In the very core, conditions may be so intense that even neutrons break apart, giving rise to quark matter, a phase of existence still not fully understood. Neutron stars are laboratories of physics that cannot be replicated anywhere else. And yet, despite their alien nature, they are also quietly beautiful. Through telescopes they appear as faint points of light, or as radio pulses captured by giant dishes scanning the sky. They do not announce themselves with brilliance like supernovae, nor with menace like black holes. Instead, they whisper across space in regular beats, the heartbeats of dead stars still echoing long after their parent has gone. Neutron stars also influence their surroundings in profound ways. Their magnetic fields can accelerate particles to near light speed, creating jets and arcs of radiation. In binary systems where a neutron star orbits a companion, it may siphon matter from its partner, forming an accretion disk that glows fiercely in X-rays. These X-ray binaries reveal some of the most dynamic interactions in astrophysics, where gravity, magnetism, and motion combine in spectacular displays. Some pulsars even serve as natural navigational beacons. Because their signals are so precise, spacecraft can use them much like GPS satellites, triangulating their position in space by timing the pulses. It is a remarkable thought. Dead stars, thousands of light years away, guiding human exploration through the galaxy. The fates of neutron stars vary. Some spin down slowly over millions of years, their pulses fading as their energy drains away. Others may merge with companions, producing gravitational waves that ripple across space-time and can be detected by instruments on Earth. These collisions are also responsible for creating some of the heaviest elements in the universe, such as gold and platinum. When two neutron stars spiral together and merge, they unleash a kilonova, a burst of light and radiation accompanied by the creation of precious metals. In this sense, the rings on human fingers and the circuitry in electronics are linked to the distant collisions of stellar remnants. The poetry of neutron stars lies in their dual nature. They are remnants of death, yet they are also creators, shaping galaxies with their magnetism, enriching space with heavy elements, and offering us cosmic timekeepers of extraordinary precision. They are extreme yet orderly, violent yet calm, distant yet deeply connected to our own existence. If stars are thought of as storytellers, then neutron stars are the echoes of their final words. They remind us that even endings can have resonance, that the collapse of one thing can give rise to something entirely new. They're quiet beacons in the night sky, each pulse a reminder of the strange beauty that emerges when the universe tests its own boundaries. To gaze at the light of a pulsar or imagine the density of a neutron star is to feel both awe and calm, awe at the sheer strangeness of matter compressed to such extremes, and calm at the rhythm of their pulses, steady and unwavering across the vastness of space. They are the universe's metronomes, keeping time long after their parent stars have burned away. In the end, neutron stars and pulsars are both mysteries and guides. They belong to a realm beyond human experience, yet their presence helps us measure, explore, and understand the cosmos. They remind us that even in death, stars do not fall silent. They continue to spin, to shine, and to shape the universe. Their voice is transformed but never entirely lost. And perhaps that is their greatest gift. The quiet assurance that nothing in the universe is ever truly gone, only changed into a new and extraordinary form. There are endings in the universe that are bright, dazzling, and filled with spectacle. A supernova can light up a galaxy, a kilonova can shower the cosmos with gold, and a pulsar can spin with unearthly precision. Yet among all the fates of stars, one stands apart in its quiet finality. This is the birth of a black hole, the point at which gravity claims total victory and nothing, not even light, can escape. The story begins in the heart of a truly massive star, far heavier than our Sun. As it nears the end of its life, it burns through its nuclear fuel at a reckless pace. Hydrogen gives way to helium, helium to carbon, carbon to oxygen and silicon, until at last it produces iron in its core. And iron is the end of the road. Fusion of iron consumes energy rather than releasing it, and so the star's furnace sputters and dies. Gravity, patient and relentless, seizes the opportunity. The collapse is sudden. In less than a second, the iron core implodes under its own immense weight. If the mass of the collapsing core is great enough, no known pressure, not even the quantum rules that hold up neutron star, can withstand it. The core crushes inward past the limits of matter itself, shrinking into a point of infinite density, a singularity. Around it forms an event horizon, the boundary from which nothing can return. A black hole is born. From the outside, the process is almost paradoxical. The collapse is violent beyond imagination, yet the black hole itself makes no sound, no light, no announcement. It simply appears, a dark void in space where once a star blazed. The event horizon is not a physical surface but a threshold. Cross it, and escape becomes impossible. Not even light, the fastest traveller in the universe, can outrun gravity's pull. To distant eyes, the star has vanished into silence, leaving only the memory of its explosion and the ghostly tug of its gravity. And yet black holes are not empty. They are the most extreme objects in the cosmos, regions where space and time themselves are bent into strange new shapes. Near the event horizon, time slows relative to the outside universe. An observer falling inward would never be seen to cross the horizon. Instead, they would appear frozen in place, their light stretched and reddened until it faded away. Inside, physics as we know it breaks down. Equations diverge, and the familiar rules of matter, energy, and space dissolve into mystery. The scale of black holes varies enormously. Some are only a few times the mass of the Sun, the quiet remnants of individual stars. Others, found at the centres of galaxies, contain millions or even billions of solar masses, their origin still a puzzle. But no matter their size, they share the same essential nature, regions of space-time where gravity rules absolutely. It is tempting to think of black holes as cosmic destroyers, swallowing everything around them. In truth, they are more subtle. A black hole does not suck in matter indiscriminately. A planet or star at a safe distance will orbit just as it would around any other massive object. Only those that stray too close risk being torn apart. When matter does fall in, however, the results can be spectacular. Gas spiraling toward a black hole forms an accretion disk, heating to millions of degrees and emitting powerful X-rays before crossing the horizon. Jets of energy can blast outward from the poles, reaching across light years. Ironically, the regions around black holes are some of the brightest in the universe. The birth of a stellar mass black hole is both an end and a beginning. For the star, it is the final chapter, the collapse into an abyss from which it will never return. For the cosmos, it is the creation of a new and mysterious object, one that will endure for unimaginable lengths of time. Black holes do not fade easily. Left alone, they persist, silent and patient, slowly evaporating only through the faint trickle of Hawking radiation, a process so slow that a black hole of stellar mass would take longer than the current age of the universe to vanish. Our own galaxy is littered with these silent remnants. They reveal themselves not through direct sight, but through their influence. A star orbiting nothing, a swirl of X-rays where no star is visible. These are the signs of a hidden black hole. Dozens have been detected in this way, and there are likely millions more wandering unseen. Each one is a monument to a star that once lived, burned, and collapsed into darkness. For all their mystery, black holes are also essential to the story of the universe. They shape the evolution of galaxies, their immense gravity sculpting the motions of stars and gas. Supermassive black holes at galactic centers act as engines, regulating star formation and driving vast outflows of energy. Without them, galaxies might look very different. Even the quiet stellar black holes born from individual stars enrich the universe with their strange presence, linking the lives of stars to the deep fabric of space-time. There is something humbling in the thought that gravity alone can achieve such triumph. No exotic forces, no hidden mechanisms, just the simple pull of mass upon mass, given enough time and weight, can reshape the cosmos so completely. From the dance of planets to the fall of an apple, gravity works quietly, invisibly, yet its final expression is the black hole, a place where even light cannot resist. For humans, black holes hold a fascination that borders on the mythical. They are the modern abyss, the dark unknown lurking at the edge of knowledge. They remind us that the universe still keeps secrets, that even with all our equations and telescopes, there are places where understanding falters, and yet they also inspire curiosity, imagination, and wonder. The idea that matter can collapse so completely, that time itself can be twisted, is both unsettling and deeply compelling. In the end, the birth of a black hole is not just the story of gravity's triumph, but of transformation. A star that once shone across the galaxy has collapsed into something new, something invisible yet powerful, silent yet commanding. Its light is gone, but its presence remains, etched into the fabric of space-time. When you look into the night sky, you will not see them. They do not twinkle like stars or glow like nebulae, but they are there, scattered among the constellations, invisible guardians of the cosmos. They are the graves of stars, and yet also their legacy, proof that even in the darkest abyss the story of the universe continues. The quiet birth of a black hole is not an ending in despair, but a reminder of the universe's patience and depth. Stars may die, but their remnants shape galaxies, bend time, and remind us that the cosmos is as mysterious as it is vast. Gravity, in its unhurried persistence, writes the final line, and the result is an object that challenges our imagination and invites us to wonder what lies beyond the horizon of sight. Every breath you take, every step you walk, every thought that passes quietly through your mind, all of it is woven from the ashes of stars. The iron that carries oxygen in your blood, the carbon that forms the backbone of every molecule of life, the oxygen that fills your lungs, and the calcium that strengthens your bones were all forged in the hearts of stars long gone. The story of life is inseparable from the story of stellar death and renewal, and to understand what we are made of is to realise that we are, in the most literal sense, children of the cosmos. In the earliest moments after the Big Bang, the universe was astonishingly simple. It was filled almost entirely with hydrogen and helium, with only trace amounts of lithium. There were no heavier elements, no carbon, no oxygen, no iron. Left that way, the cosmos would have been sterile, a vast cloud of light gases drifting forever. Complexity, chemistry, and life itself required a new source, and that source was the stars. Stars are the great forgers of creation. In their cores, hydrogen is fused into helium, and as they age, helium fuses into carbon and oxygen. Larger stars carry the process further, producing neon, magnesium, silicon and iron in their onion-like interiors. But the heaviest elements, those beyond iron, demand something more extreme, the catastrophic conditions of supernovae or the collisions of neutron stars. In these fiery crucibles, gold, platinum, uranium, and other heavy elements are born. Without the violence of stellar death, the universe would lack the materials that shape worlds, machines, and living bodies. Take the iron in your blood, for example. Each hemoglobin molecule in your red blood cells contains iron atoms at its core, allowing it to bind oxygen and deliver it to your tissues. Without iron, life as we know it could not exist. And yet, iron cannot be made in ordinary stars as part of their stable burning. It appears only in the final moments of massive stars, created in their cores and then scattered by supernovae. Every drop of blood flowing through your veins is a gift of those ancient stellar explosions. Or consider carbon, the foundation of biology. Carbon's ability to form 4 bonds makes it uniquely versatile, capable of building chains, rings, and complex molecules that fold into proteins and spiral into DNA. Stars created carbon through the fusion of helium, a process that seemed almost impossible until a peculiar resonance made it possible. Without that resonance, carbon might never have formed in abundance, and the chemistry of life could not have arisen. The fact that it did speaks to the remarkable pathways carved out by physics in the depths of stars. Oxygen, the gas you breathe with every inhalation, is another stellar gift. Produced in the cores of massive stars, it now fills Earth's atmosphere, bound into water, plants, and your own cells. Silicon, born in stellar interiors, forms the minerals beneath your feet and the microchips in your devices. Calcium, created in dying stars, builds the framework of your skeleton. Even the trace elements essential to life, zinc, copper, iodine, have their origins in stellar furnaces and violent explosions. To list the elements of your body is to recite the history of stars. The distribution of these elements across the universe is a story of constant recycling. Stars form from clouds of gas enriched by earlier generations, live out their lives, and return material to space when they die. The next generation of stars forms from that enriched gas, bringing new planets and new opportunities for life. Each cycle adds more complexity, more variety, more possibilities. The galaxy we live in has been shaped by billions of such cycles, each one leaving behind the seeds of the next. Earth itself carries the imprint of this process. The rocks that form mountains, the oceans that lap against shores, the air that fills the sky. All are the products of stellar alchemy. Even the gold adorning human fingers and the silver in coins and mirrors are remnants of cataclysmic events that happened billions of years before the sun was born. To hold a piece of metal is to hold the memory of a star's violent end. It is extraordinary to realize how intimately connected we are to this cosmic story. When ancient humans looked up at the stars and told stories of gods and heroes, they were unknowingly seeing their own origins written across the sky. The myths may have been imaginative, but the truth is even more profound. Those stars were not just lights above, but the very ancestors of human bodies and minds, and the process continues. The Sun, steady and modest as it is still producing helium from hydrogen in its core. One day, when it swells into a red giant and releases its outer layers, it will return carbon and oxygen into the galaxy. Those elements will enrich future clouds, from which new stars and planets will form. In this sense, even our Sun will join the cycle of creation, contributing to the chemistry of life elsewhere. Some scientists call this idea cosmic recycling, but the phrase hardly captures the poetry of it. It is not just that matter is reused, but that matter is reborn into new forms, new worlds, and new possibilities. The carbon that once drifted inside a dying star is now folded into the spiral of your DNA. The oxygen that flared from a supernova now fills your lungs. The calcium scattered by an ancient explosion supports the weight of your steps. Every part of you carries the history of countless stellar lives. There's also a sense of continuity in this story that can be oddly comforting. Stars may die, but they do not disappear. Their matter remains, reshaped and repurposed, flowing into the next generation. Life itself is part of this flow, emerging not as something separate from the cosmos, but as one of its natural outcomes. To exist is to participate in the legacy of stars. From a philosophical point of view, this realization reshapes how we think about our place in the universe. We're not outsiders peering in. We are made of the very stuff of the cosmos, and our consciousness is the cosmos reflecting on itself. When you look at the stars, you're seeing not just distant suns, but the raw materials of your own being. Their light is not merely something to admire. It is a reminder of the deep connection between matter and life. The next time you pause to breathe, to feel your chest rise and fall, remember that the oxygen filling your lungs was once locked inside a star. The next time you feel your heart beat, remember that its rhythm is carried by iron atoms forged in stellar cores. The next time you touch the ground, remember that the calcium in your bones was shaped in explosions long before Earth existed. These are not poetic metaphors. They are literal truths written into the chemistry of existence. The legacy of stars is not simply that they light the night sky, but that they give substance to everything around us and within us. They are the reason mountains rise, rivers flow, forests grow, and animals breathe. They are the reason we can think, wonder, and ask where we came from. They are the quiet architects of life, working across billions of years to build a universe capable of contemplating itself. Every atom in your body is a relic of this history. Every breath, every heartbeat, every step is a continuation of the work of stars. And though they may seem distant, they are as close as your own hands, your own thoughts, your own existence. You're not separate from the stars. You're their legacy, their living continuation, a reminder that even in death, the cosmos creates. For as long as humans have tilted their heads back and looked at the night sky, stars have been more than distant points of light. They have been symbols, companions, and guides. Long before telescopes revealed their true nature as burning spheres of plasma, stars were woven into stories, etched into myths, and trusted as navigators across seas and deserts. The science of stars explains how they live and die, but the human imagination has always supplied another layer of meaning, one that makes the night sky a tapestry of culture as much as of physics. In many ancient civilizations, stars were thought to be divine. The Egyptians aligned temples and pyramids with the rising of certain stars, believing them to be the homes or manifestations of gods. The star Sirius, the brightest in the night sky, was especially important. Its annual rising in the dawn coincided with the flooding of the Nile, the event that made agriculture in Egypt possible. For them, Sirius was not just a star, but a messenger of life, renewal, and the gods' benevolence. To the Greeks, stars were the immortalized forms of heroes and myths. Orion the Hunter was placed among the constellations, accompanied by his loyal dogs, Canis Major and Canis Minor. The story of Perseus and Andromeda sprawled across the sky, frozen in starlight. These constellations served as reminders of courage, tragedy, and divine intervention. In their placement, the Greeks found meaning, as though the heavens themselves had recorded the stories that defined their world. The Chinese sky was mapped in its own intricate way. Instead of 12 constellations, the Chinese tradition included hundreds, with stars grouped into detailed asterisms reflecting emperors' courts, rivers, markets, and legendary figures. The sky was a celestial mirror of earthly life, a record of harmony between heaven and earth. For centuries, astronomers at imperial observatories charted the heavens not only to understand celestial rhythms, but also to divine omens for rulers. A new star appearing, what we now recognize as a supernova, might be interpreted as a warning to an emperor, or the sign of a new mandate from heaven. The Polynesians, masters of ocean navigation, saw stars not as gods or myths, but as tools. For them, the night sky was a map. Navigators memorized the rising and setting points of hundreds of stars, using them to cross thousands of miles of open ocean without instruments. Canoes travelled from island to island, guided by the steady rhythm of starlight. To the Polynesians, stars were companions of the journey, reliable markers that ensured survival. Their knowledge of the sky was so precise that it rivaled any modern navigation system, built on observation, memory, and trust in the constancy of the stars. In other traditions, stars were symbols of fate. Astrology, practiced in various forms across cultures, treated stars and planets as influences on human lives. The Babylonians charted the motions of the heavens and saw in them the patterns of destiny. To them, the positions of stars were not random, but a cosmic script, guiding the fortunes of kings and commoners alike. Even today, horoscopes trace their lineage back to those ancient skies, reflecting a long-held belief that the universe and human life are bound together. For indigenous peoples across the world, stars have served as anchors of story and time. The Lakota spoke of the star people and wove star maps into their spiritual traditions. The Aboriginal Australians created some of the oldest surviving star lore, seeing in the dark patches of the Milky Way the figure of an emu, a story that stretched across cultures and continents. These stories did more than explain the stars. They preserved knowledge of seasons, migrations, and survival. Myth and meaning carried practical wisdom, ensuring continuity across generations. What is striking is how universal the fascination with stars has been. In every culture, in every time, humans have looked up and seen not just distant suns, but reflections of themselves. Stars have been protectors, storytellers, guides, and judges. They have been signs of harvests and portents of war, symbols of hope and of loss. Even falling stars, meteors streaking through the atmosphere, became wishes or omens, sparks of magic in the night. The persistence of these stories speaks to something deep in human nature. To look at the stars is to confront both vastness and mystery. The sky's too immense to ignore, too beautiful to dismiss, and too constant to be irrelevant. It is natural that people, long before science, filled that space with meaning. And in doing so, they made the stars part of human life, bridging the gap between the eternal and the everyday. Science has since peeled back the veil, showing us that stars are not divine beings or fixed points of fate, but natural objects governed by physics. And yet, this knowledge has not stripped away their wonder. If anything, it has deepened it. To know that the light from Orion's belt left its stars more than 1,000 years ago, or that the atoms in your body were forged in ancient stellar furnaces, is a revelation as profound as any myth. The stars may no longer be gods, but they remain sacred in another sense, as the origin of all that exists. Even in modern times, stars carry symbolic weight. They adorn flags representing unity, aspiration, and identity. They guide astronauts as they once guided sailors. They inspire music, art, and poetry. The phrase, "to reach for the stars," still conveys ambition and hope, a metaphor for striving toward the seemingly impossible. The stars, though distant, continue to shape human imagination as much as they ever did. Perhaps what makes stars so powerful in myth and meaning is their duality. They are constant yet changing, familiar yet unreachable, eternal to the human eye yet fleeting on cosmic timescales. They are both part of nature and beyond ordinary experience. This tension invites story, symbol, and reverence. To see the stars is to be reminded of limits and possibilities, of smallness and connection. And so the legacy of stars is not just physical in the atoms they provide, but cultural in the meanings humans give them. The stories of gods and heroes, the maps of navigators, the symbols of fate, and the metaphors of poets all show that stars are as much a part of human culture as they are of the cosmos. The night sky is not empty. It is filled with the voices of countless generations, all finding themselves reflected in the distant light. When you next gaze upward, it is worth remembering both truths at once. Stars are vast nuclear furnaces, burning through their fuel, living and dying according to the laws of physics. And stars are also the myths of Ryan and Sirius, the guides of Polynesian navigators, the emu in the sky of Aboriginal Australians, the signs that once marked the rise and fall of kings. They are science and story, fact and symbol, reality and meaning woven together. This blending of imagination and knowledge is perhaps the most human response of all. We live in a universe that is both understandable and mysterious, both physical and poetic. Stars embody that balance. They are reminders that we are part of something greater, that the cosmos is not only measurable, but meaningful. And whether seen as gods, guides, or guardians, they continue to shine above us, steady lights carrying both truth and story across the vast dark. When a star reaches the end of its life, whether in the quiet fading of a white dwarf or the thunderous finale of a supernova, it does not vanish into nothing. Instead, it gives itself back to the cosmos. The gases and elements it created over millions or even billions of years are cast out into the interstellar medium, enriching the great clouds of dust and hydrogen from which new stars are destined to emerge. In this way, every stellar death becomes part of a much larger rhythm, a cycle of endings and beginnings that stretches across the galaxy. The night sky, with its countless twinkling points of light, is a living record of this cycle. Many of the stars you see tonight are not the first generation born from the raw simplicity of hydrogen and helium that filled the universe after the Big Bang. They are descendants, formed from material already enriched by the lives and deaths of older stars. When you look at a star, you are seeing not only the present but also the memory of earlier cosmic generations written into its very atoms. The process begins with the return of matter to space. In the case of smaller stars, this return comes gently. As they swell into red giants, their outer layers drift outward, carried away by stellar winds until they form glowing shells of gas, planetary nebulae illuminated by the fading white dwarf at their centre. These nebulae shine with vivid colours when seen through telescopes, glowing greens and reds that mark the release of elements into space. It is a star's quiet farewell, but also a gift because those elements, carbon, nitrogen, oxygen, will someday be woven into new clouds, new stars, and perhaps new forms of life. For massive stars, the return of matter is far less subtle. When they end in supernova, they fling vast quantities of gas and heavy elements into space with tremendous force. Shock waves from the explosion ripple outward, stirring nearby molecular clouds and compressing them until new regions collapse under gravity. In this way, the death of one massive star can directly trigger the birth of many others. Stellar death becomes stellar midwifery, the violent end of one life catalyzing the gentle beginnings of countless more. The Crab Nebula is one of the most famous examples of this process frozen in time. What astronomers see today, a sprawling cloud of delicate filaments expanding across space, is the remnant of a supernova witnessed nearly 1,000 years ago. Within its tendrils lies not just the memory of a star's destruction, but the seeds of new formation. Over time, those gases will drift and mix, adding richness to the galaxy's star-forming regions. Nothing is wasted. Indeed, the very clouds where new stars form are often patchworks of material from countless stellar ancestors. The Orion Nebula, one of the brightest and most studied nurseries, glows with the fingerprints of stars long gone. In its vast pillars and wisps, enriched gas collects, cools, and collapses into new suns. Some of those stars may one day host planets with oceans and atmospheres, where life could look up at their parent star and wonder where it came from. The answer would be simple and profound. It came from the ashes of older stars. This cycle is not merely poetic, it is essential. Without the enrichment provided by dying stars, the universe would still be little more than hydrogen and helium. Complex chemistry, the kind that builds planets, rocks, atmospheres, and eventually living cells, depends on the recycling of stellar matter. Carbon for organic molecules, silicon for minerals, iron for cores of planets, phosphorus for DNA, calcium for bones. All of it has passed through the life cycle of stars. It is a reminder that destruction in the cosmos is rarely wasteful. Instead, it is transformation. The galaxy itself bears the imprint of this process. Regions heavy with new stars glow brightly, their light reflecting off the dust and gas around them. Other regions, long past their star-forming days, appear quieter, populated mostly by older, redder stars. Astronomers can read these signs as though they were chapters of a book, seeing where the cycle is active and where it has slowed. Galaxies evolve through the continual interplay of birth and death, each generation enriching the next. Even our own sun is part of this cycle. It was born around 4.5 billion years ago in a molecular cloud enriched by earlier supernovae. The evidence lies in the elements of Earth itself. Isotopes of certain elements in ancient rocks suggest that a nearby supernova may have contributed directly to the material that formed the solar system. The Sun, the Earth, and every living thing here carry the legacy of a long chain of stars that came before. It is humbling to realize how many cosmic lives had to end for life on Earth to begin. Dozens, perhaps hundreds, of ancient stars burned, fused, exploded, and scattered themselves across the galaxy so that the ingredients of water, stone, atmosphere, and biology could collect into one small blue world. Life itself is the most intricate expression of the stellar cycle, the universe finding a way to organize atoms forged in fire into beings capable of reflecting on the stars that made them. The endless cycle also ensures the universe remains dynamic. Without the recycling of stellar matter, galaxies would eventually run out of the dense clouds needed for star formation. They would grow dimmer, filled only with old, fading stars. Instead, the death of stars continually replenishes and stirs the interstellar medium, keeping galaxies alive with the promise of renewal. Stars, in this way, are not just individual actors, but part of a greater community. Their deaths feeding the future in ways both visible and invisible. From a human perspective, this rhythm carries a strange comfort. We tend to think of endings as final, as losses without return. Yet in the cosmos, endings are rarely so absolute. The death of a star is not the loss of its matter, but its redistribution. What seems like destruction is simply another step in the transformation of elements, another handoff in a process that stretches across billions of years. Even the heaviest elements, born only in the most violent collisions and explosions, eventually find their way into the cycle. Gold and platinum from merging neutron stars may seed future worlds with metals that glint in jewelry or drive technologies. Uranium scattered by supernovae may power the heat of planets and influence geology for billions of years. The gifts of dying stars are as practical as they are beautiful. The cycle continues endlessly, with no single star truly isolated from the whole. A star lives, burns, and dies. Its remains drift into space, mix with other remains, and collapse into new stars. Those stars shine, warm planets, and eventually pass their materials on again. Across billions of years, this process stitches together the fabric of the galaxy, binding stars and worlds into a continuous chain of creation. When you stand beneath the night sky, you're not only looking at stars that shine in the present, you are seeing participants in an ancient relay, each one carrying forward the light and matter of those that came before. The universe is not static, it is a cycle of inheritance, a story where every star is both heir and ancestor. In the end, the greatest legacy of stars may not be their brilliance or their grandeur, but their continuity. They remind us that life, matter, and even beauty are never truly lost. They're transformed, passed along, and reborn in new forms. The light of the stars you see tonight carries the memory of generations, and the atoms of your own body are part of that memory too. The endless cycle of stars giving birth to stars is both science and poetry. It explains the chemistry of the universe, but it also offers a philosophy of renewal. It tells us that nothing is wasted, that even death is folded into creation, and that every spark of light in the sky is part of an unbroken chain, stretching back to the dawn of time and forward into futures we cannot yet imagine. From the moment the first stars flickered into being, the universe has never been the same. What began as a cosmos of almost pure hydrogen and helium, silent and simple, became alive with light. With each ignition, stars wrote a new chapter in the story of existence, not with words but with photons, elements, and time itself. They have been the steady companions of galaxies, the architects of planets, and the invisible ancestors of life. To reflect on stars is to reflect on the quiet engines that have shaped everything we know. They are not loud in their work. Most stars do not end in explosions that rock the heavens. The vast majority spend their lifetimes in calm equilibrium, fusing hydrogen into helium with unwavering patience. This steady balance between gravity pulling inward and energy pushing outward is the rhythm that defines the cosmos. For billions of years, a single star can shine with such constancy that it becomes easy to forget the sheer improbability of its endurance. That steadiness is the gift upon which life depends. Without it, there could be no stable warmth, no gentle seasons, no oceans or forests, no time for complexity to take root. Our Sun is one such star, modest in size and lifespan compared to others, but extraordinary in what it makes possible. It is not a giant, nor a dwarf of immense longevity, but a middle-aged star in the quiet fullness of its main sequence. Yet from its steady glow has come the entire story of Earth, from the earliest microbes stirring in ancient seas to the civilizations that now gaze upward at the stars and wonder about their own origins. The Sun is proof that ordinary stars can become extraordinary by virtue of their companionship. The life of a star is also a lesson in patience. From the slow collapse of a nebula into a protostar, to the billions of years spent in calm fusion, to the gradual changes of aging, every stage unfolds on timescales that dwarf human comprehension. Stars remind us that existence does not always rush. It unfolds steadily, layer by layer, cycle by cycle. Even their deaths, though sometimes violent, are part of a greater rhythm that ensures renewal. A white dwarf cooling in silence, a red giant puffing its layers into space, a supernova scattering elements across a galaxy. Each ending becomes a beginning elsewhere. Through these processes, stars become the alchemists of the universe. They forge the elements that make worlds possible: carbon for life, silicon for rocks, iron for blood, oxygen for breath. In their deaths, they release these elements into the interstellar medium, enriching the great clouds of gas and dust that give rise to new generations of stars. Nothing is wasted. Every atom of your body has passed through this cycle, through the core of a star, through a cloud, through the collapse and birth of new suns. You are quite literally made of starlight condensed into living form. And the cycle continues. Look at a nebula glowing faintly in the night sky, and you see the cradle of new stars. Look at a white dwarf or a neutron star, and you see the memory of a life once bright. Look at a black hole, and you see gravity's ultimate triumph over matter. Every point of a light in the sky is part of this unending story. Some just beginning, others long past their prime, all part of a continuum that links past to future. Yet stars are not only physical, they are cultural and symbolic too. For millennia, people have looked at them as guides, gods, or omens. The same stars that powered the chemistry of life also inspired the myths of Orion, Sirius, and the Milky Way. They helped sailors cross oceans, marked the rhythms of agriculture, and filled human imagination with wonder. Even now, when science explains their nature in exquisite detail, they remain metaphors for hope, ambition, and eternity. We still speak of reaching for the stars, of wishing on them, of finding meaning in their light. They are both fact and story, science and symbol. In this way, stars remind us of our dual nature as thinking beings. We are made of their atoms, bound by their physics, and illuminated by their light. Yet we are also dreamers, seeing in them patterns, myths, and signs. The night sky is not just a scattering of distant suns, it is a mirror of humanity's imagination, layered with centuries of meaning. And both truths coexist without conflict. To know that Orion's belt is a trio of stars hundreds of light years away does not erase the myth of the hunter. It deepens it, layering reality onto story in a way that makes the sky richer, not poorer. As you sit beneath the night sky, it is easy to feel small. The stars are so numerous, so far away, and their lifetime so vast that human existence seems fleeting by comparison. And yet, the connection between us and them is intimate. The light from a star may take hundreds or thousands of years to reach your eyes, but the atoms in your body took billions of years to form, shaped by generations of stars that lived and died before the sun was born. The stars are not distant strangers, they are family. There is also a quiet reassurance in their steadiness. Whatever happens on Earth, the stars continue their slow cycles, unbothered by human concerns. They burn, they change, they fade, but they do so with patience beyond measure. To watch the stars is to step into a rhythm larger than yourself, one that spans billions of years and countless generations of suns. In their presence, the urgency of daily life softens, replaced by the sense of belonging to something much greater. And so the story of stars is not just astrophysics, it is the story of existence itself. It is the story of how the universe became rich enough for life, how matter found form, and how consciousness arose to reflect on its own origins. Stars are the thread stitching together past and future, matter and meaning, science and story. They are the quiet engines that make the cosmos dynamic, alive, and full of possibility. Every night sky is filled with this story. The light of newborn stars in nebulae, the glow of middle-aged suns like our own, the faint shimmer of ancient giants nearing their end, all of them are part of an unbroken chain. To look upward is to see billions of lives unfolding in slow motion, a theatre of beginnings and endings that plays on scales of time too vast for any one species to fully grasp. And yet, somehow, we are part of it. Our lives, brief as they are written from the same stardust. Perhaps that is the most calming truth of all. You're not separate from the stars you see above. Their light falls on your eyes, their atoms flow in your veins, their cycles echo in your heartbeat. To live is to participate in their legacy, to be part of the quiet cosmic rhythm that has been unfolding since the dawn of time. Stars may seem distant, but they are as close as your breath. So when the day ends and the night sky opens above you, take a moment to pause. Let the light of the stars remind you of their patience, their endurance, and their gift. Every twinkle is a message from across space and time, a reminder that creation is ongoing, that endings are beginnings, and that you are part of a story far larger than yourself. Stars are not just decorations on the canvas of the night. They are the reason the canvas exists at all. They are the fire, the memory, and the promise of the cosmos. Quiet, Constant and enduring, they continue their work, generation after generation, building a universe capable of wonder. And as long as they shine, the story goes on. A calm, steady rhythm written in light, in matter, and in life itself.